One. Well, hello everyone. Welcome to the second episode of the 2021 Dynamic Walking Meeting. I'm so pleased to be here on behalf of myself and my co-organizer, Greg Sawicki. We're very excited about the lineup of speakers, moderators, panelists, and posters that we have for you today. Okay, and of course we have to thank we have to thank our Sorry, I'm hearing myself on audio over YouTube. That was very freaky. So, hello, I'm back. So, anyway, I wanted to thank our organizing team, who this would not be possible without all their help. So, thank you very much to all of these folks for making this happen. So today is our second episode, which focuses on the concept of neural control. Neural for the bio side, control for the robotic side. Basically, everything control is the theme of this meeting, okay? And we're very pleased to have this lineup for you today. So we're going to start our first session in just a minute. A few notes for everyone here. Everyone here on Zoom, thank you for being here. If you have a question for these speakers when they're going, you have two options I would recommend. One, post your comment in the chat. We will be watching the chat, and we will be, and the moderators will have those questions available to them if they come up during the Q&A. And number two, you can raise your hand using the raise hand feature, and the moderators will see that on the participants list. Okay. Number two, this is also being broadcast live to YouTube. So hello everyone on YouTube out there. We could actually see your comments too, and they will be forwarded into the Zoom chat. So even if you can't be in the Zoom session with us, you can still participate. So please be aware of that. And finally, in between sessions, there's the spatial chat, which many of you have found. I will include the spatial chat in the link in the chat below, so everyone has access to it for ease and convenience. So without further ado, I want to switch over to our first moderator. So let me add a pin in him. And so today, we're thrilled to have Dr. Patrick Wensing here, who's an assistant professor in the Department of Aerospace and Mechanical Engineering at the University of Notre Dame, where he directs the Robotics Optimization and Assistive Mobility Lab. What a great series of expertise to have for moderating this panel. So without further ado, Patrick, could you just take it away?
Yeah, thank you very much, Christian. I'm very excited for our panel today, and I'm excited to introduce our first speaker, Dr. Michael Posa. Michael's an assistant professor at the University of Pennsylvania, and today he's going to be telling us about the dynamics of contact events and methods for helping our robots handle them more gracefully. Michael?
Thank you very much, Patrick. Hopefully everyone can see my screen. So why don't I jump in, because we have limited time here. Super excited to be here. Thank you very much to the organizers for putting together the workshop. As always, dynamic walking is one of my favorites. So, we've been working on some various things in the lab, including jumping, which we'll come back to. But let's sort of start at looking at this this landing motion here, and kind of inspired by this basic question here: what happens when the robot hits the ground? And it doesn't matter, right, what we do when the robot hits the ground. So we'll take a toy problem here. We'll think about a rimless wheel. And we'll suppose this rimless wheel hits the ground with both feet at the same time with some initial velocity. If you want to sort of resolve this impact event, right, both feet landing simultaneously, it turns out the answer sort of depends on which one hits first, right? If A hits first or B hits first, you can get rock to the left or you can rock to the right. And there's this notion of potential non-unique solutions that can arise from this motion. And in fact, David Remy, right, had this great talk, for those of you who remember, back in 2016 at Dynamic Walking, later followed up with a journal paper, discussing these ambiguous possible outcomes that arise in locomotion, even without simultaneous landing events. So this slide will be a little story of the role of multi-impacts in dynamic walking in particular. And then so, this kind of goes back to some of my earlier work, right, and way back in 2012, thinking about, how do you plan through multi-contact motion? And in fact, if you look at what a planner does, even if there's multiple ambiguous outcomes possible, planners actually act optimistically. They sort of assume often that they can pick from the possible multi-impact outcomes, which may or may not be a good idea. Typically, those sort of non-uniqueness is being driven by uncertainty in some sense. And then a student in my lab, Matt Halm, a couple of years ago, discussed an approach to set valued mappings for these impacts. And today I want to sort of discuss our follow-up work to that, which I think is sort of the concluding story here to how to think about multi-impacts. I think this is something we've been thinking about for many years and are finally done. So I'm happy to sort of say that I think we have more or less the answer here. And the principle to deal with non-uniqueness is to capture all possible outcomes, right? And just to be able to describe what might happen. And so we've come up, really Matt has come up with this differential inclusion model where sort of the details are up here, but this is a single differential inclusion that describes impact and continuous dynamics. You can think of the cartoon here on the right as essentially describing the process where if you're in the air, there's some nice continuous dynamics. This is for a point mass falling, okay? Then there's this kind of impact event, which occurs when you're right on the surface of the ground and your velocity would be penetrating. And you can think of an inclusion as sort of the impact starts here and terminates up here, and some pseudo time elapses in between. And then off to the left-hand side is everything that involves penetration. And we define, for completeness, a differential inclusion over there, but in fact, that can prove that's not reachable. Okay, so the net result of the story here, to be concise, is we have a single inclusion for multi-impact for continuous dynamics and impacts. We can prove that solutions always exist. We can prove that time always progresses. So we sort of pause time during impact events, but it will always restart at some point. Penetration can't occur. And in many ways, you can think of this as a generalization of standard hybrid and LCP-based models. Okay? Not a great computational technique for something like pure simulation, because it's an inclusion and how do you simulate an inclusion? But it's really nice for things like set valued analysis. So for instance, one thing we can do is we can actually sample from the inclusion. We can simulate an LCP, and now we can actually compute possible post-impact sets. So something like that rimless wheel example, or something like a billiard break for pools, or in this case, an example inspired by David Remy's paper. We can look at these impact events, take some samples and simulate and say, here's the set of possible post-impact velocities. Right? We can also do this thing for things like reachability or robustness analysis going down the line. So like I said before, I think this is sort of on the theoretical side of the talk today. But I think we now have a way of describing all the things that might occur in these multi-impact settings. And I think this is important because if we're thinking about planning or thinking about control or thinking about verification, we can't pretend the world is always going to behave like we want, particularly if we're doing something like jumping and landing with 2 feet on the ground at the same time. We do have to consider the possibility of non-uniqueness and the outcomes that might arise from that. So this is sort of the more theoretical side of today's talk. But this is kind of where we got started thinking about multi-impact. And then, okay, so let's go back to our jumping now. So and think about control. Okay, so we have something like Cassie landing. And the both feet, in the rigid body plan, we run trajectory optimization. The rigid body plan says both feet are going to land at the same time. There's going to be some sort of inelastic impact event. And then we're just going to immediately detect that event and we're going to switch modes, right? For people who have tried to do control on Lego robots, this sounds like a terrible idea. And we'll start by looking at some data from the event. So we have data, in fact, here from the jump of the velocities of the different joints of the Cassie robot. And the impact starts right around 0 here. This is all in milliseconds, and maybe it ends, I don't know, 20, 10, somewhere in between milliseconds. Okay, so this is sort of what our impact looks like as best as we can measure using Cassie. And it's pretty obvious here that there's not an instantaneous inelastic impact event that occurs when the robot hits the ground. You can see that in the video, right? There's this little toe tap event in the video. But in every trajectory that wheel is generated from jumping, there's some non-zero time in which impact is occurring over, right? And so this rough sort of rigid body model we started with is not really a great one. Okay, so what should we do here? So let's think about an impact event a little more carefully. So the rigid body model would say I have some post-impact velocity, and it's equal to my pre-impact velocity plus the effect of some impulse event. Right? And let's suppose I'm going to use some kind of control law, whatever it's a PD control law or some other feedback policy. Right, so this is my nominal plan. Right, I have some trajectory. I have an impact event. It jumps. Okay. Right. So, but we said that's not real, right? What's really real is that something is happening in between here, right? There's something going on during this impact, and the theoretical model from before would say there's some differential inclusion and forces are being applied in some sequence between the toes and the heels and so on. But we're not really sure what order they're occurring on. And here we're not even sure that they're both landing at the same time, right? The heel and the toe could land at different times. There's some kind of impact event. And during that event, and it takes 20 milliseconds or 10 milliseconds, our velocity is somewhere in between, right? Imagine this as a 1D cartoon of high dimensional space. And so the question might be, well, if I want to do tracking control, if I pretend I'm in the pre-impact state, I get a big error. And if I pretend I'm in the post-impact state, I get a big error. And if I'm going to take this big error here and I'm going to multiply it by my gain, I'm going to get a big control effort, which is probably not really what I want here, right? So this would say, no matter what I do from a hybrid perspective, I'm going to get an error that's roughly proportional to the size of the impact. But I'm planning for a big impact, and that doesn't sound quite right. Okay, so the sort of philosophy here with this work is that the impacts are these brief high uncertainty regimes, but they're also regimes with limited sensing. So not only is my velocity somewhere in between, but I can't really promise that I can actually measure it accurately. My IMU is going nuts. All my smoothing to try to difference my positions is being problematic because it's interfering with the actual dynamics. So this is a really hard region to sense in. And so what do people do in practice? They do some kind of, they reduce their gains perhaps, or maybe they blend some pre and post impact controllers in some mechanism. There's a lot of awesome work in sim-to-real. I mean, that's amazing work going on right now. It's certainly an option, but on some level, you kind of have to know the model to do sim-to-real, right? You at least have to know what uncertainty exists in the impact event, right? Have some sort of known unknown, to quote one of our former VPs here in the US. So I think it's not totally clear what should be done. There's some really nice work actually out of Michigan very recently by Gong and Grizzle, where they said, well, look at angular momentum about a contact point for single point foot landing, and look at angular momentum. And angular momentum doesn't change during the impact. So that's sort of a nice thing to try to regulate, right? It doesn't change during impact. And we got thinking about this really Will did. It's like, can we generalize this idea, right? Can we generalize this idea of something being constant through an impact event? Okay, and so, first, I would say very strongly, feedback on velocity is very brittle. Velocity is changing incredibly quickly. We should not try to do feedback on raw velocity measurements. So you can barely measure it, much less model it. Right? Instead, let's look at the velocities that are invariant to impact events. Okay, so essentially velocities that are going to be unaffected by applying an impulse force. Again, a generalization of this idea of angular momentum, which would be a scalar or a 3D vector, 2D or 3D. And what we can see here is, while the velocity of the robot during this impact event are changing very quickly, in fact, over multiple trials, consistently changing very rapidly, if we take those velocities and we project them down into this lower dimensional space and look at that projection, so these are the impact invariant space velocities, we see that they're essentially constant during impact events. It's not changing the green one, but others are more or less flat. And so we are getting what we think, which is some lower dimensional space unaffected by impact, and we can still do feedback in this space. Okay, so we have to realize that over here, feedback is a fool's errand, right? We're just going to hurt ourselves if we try to measure and react that quickly. But if we're acting in this impact invariant space, we at least maintain some degree of controllability or control authority throughout this impact event. And so the idea is essentially to apply impact invariant feedback. We do this for something like an operational space control. You can do this for PD control. It works for essentially any kind of feedback policy you might imagine, as long as you apply this projection first. Okay, and so this is sort of what enabled our jumping in the lab. We've also sort of looked at this in simulation and seen that it adds some robustness in simulation to things like ground height variation, reduces effort spikes because you're no longer getting this gain times big velocity error term, and we're sort of excited to kind of keep pushing this forward on CASI. Okay, and then so now we've kind of said that impacts are really hard. We can model impacts nicely theoretically, but they're really hard to measure in practice. And maybe that nice theoretical model of rigid impacts is not perfect. So why don't we just learn it instead? And so here's some other work, not really like robots, but I think very relevant to the dynamic walking community, where we took a deep network and we took a bunch of tosses, here around 100 tosses of this cube in motion capture, and tried to learn it with a deep network, and it works okay. It gets sort of bulk motion right, but does really poorly at things like predicting orientation, exhibits penetration as well, and qualitatively not quite correct. So thinking about learning contact, right? There's a problem here, which is essentially that deep networks are biased in some sense. All the nice theoretical results about deep networks are biased to find simple functions, often things like smoothest interpolators to explain motion. And the real data is not smooth, okay? And we can show, I'm going to skip through this relatively quickly because I know I'm sort of running out of time. But we can show empirically that if you look at stiffness, for instance, as a single parameter here in simulation, the stiffer the data is, the harder it is to learn. No big surprise there for anyone who's thought about numerical optimization. Stiffness clearly should cause problems, but here directly derived from contact. And I would say this should be a warning sign for anyone looking at something like differentiable simulators, differentiable physics as a tool of choice. If your differentiable simulator is nice and stiff, like the real world, it's going to behave poorly. If you soften it artificially, are you really getting meaningful results? I think there's an open question there. Alternatively, what we've done is try to embed notion of discontinuity. Oops, I have the wrong video here. Try to embed notion of discontinuity into the physics learning problem, where we essentially learn things like contact geometry and contact physics. And what we get are results here that sort of blow out of the water standard deep learning approaches. So if we impose lots of structure, that's the purple line here, we can essentially figure out this cube tossing data from around 5 trials, 10 trials. If we impose a little bit less structure, we use, say, deep networks as well, we still sort of do really well at long-term prediction. And the idea here is essentially to try to separate out contact dynamics from non-contact dynamics and let deep learning do what it's best at, which is find smooth interpolators, find smooth functions, right? I'm happy to talk about the details there, but I know we're sort of out of time. And then last question here, which was, how do we learn the non-contact dynamics and contact dynamics at the same time? Can we do so? And if you think about your equation of motion, it has sort of contact part and non-contact part. It's not clear that you should be able to disambiguate the two, right? They're summed together. How do you tell which one's apart? But it turns out there actually might be hope, right? There might be hope, especially from this idea of regularization, right? This thing over here, this non-contact part, is nice and smooth, right? This thing is not. And so if we regularize it correctly, we can try to find this with the nice regularized part and then find contact derived from geometry, which is nice and smooth. And sort of takeaway here is that, in fact, we can do so. We can identify things like geometry. We're still working on the full story here. This is very much preliminary results. You'll notice there's kind of some areas of where they get confused. If you think about, let's focus on this middle plot here. Looking at force over time, predicted force over time, you have these big spikes in the contact part. So we are predicting impacts during impact events, but the non-contact part is getting a little bit muddled during those contact timings, right? So we're not getting from observation, so purely from watching these cubes roll and tumble, we're not entirely able to tell which parts of the force were contact forces and which weren't. But we do a pretty good job there. Okay, and so lastly, I just want to thank all the students who did the great work here, and happy to talk, take questions and advertise for some of the posters coming out of our lab later on today.
Excellent. Thank you very much, Michael. So we have one question here in the Zoom chat that we'll go with. For those that are working on your other questions, again, we'll be happy to take them via the Zoom chat on YouTube, or we can handle the old-fashioned hand raise. So our first question comes from Greg Swicky. Animals often enter ground contact with a good deal of co-activation of muscles around distal joints. Some might say this is indicative of an impedance control strategy. What is Cassie trying to control? Force, position, other? i.e., what is the objective of the controller in and around impact?
Yeah, that's a really great question, Greg. And I would really also sort of be curious to see what the OSU folks are deriving from their control policy around impact event. What we're seeing here is essentially that the velocity components of the gains there. So we're controlling force, right, and measuring state, but the velocity components in particular, the feedback on velocity has to be low to generate this robustness. But at the same time, what we're trying to say is, well, don't drop all of the gains down to zero. Try to keep some if you can, right? The ones that are even unaffected by impact events. So swing legs or this kind of impact invariant subspace, so to speak. But I think there is a broader question there, right? Which is, if you don't know where the ground is and you have this great deal of uncertainty, right? Can we generate controllers that are robust to that? And that's where we want to go. I think the thing we don't really know yet that we're trying to answer right now is what form does this uncertainty really take, right? I think what we're looking at right now is that impact event itself. And what we've seen is that you can't pretend it's instantaneous. Okay, it's just not true. And in fact, even if it's really quick, it's 5 milliseconds, 10 milliseconds, and you do pretend it's instantaneous, your controller can do bad things. Right? It seems like a tiny amount of time, but it's plenty long enough for your controller to act up and knock yourself over. So we want to understand uncertainty, and if the hope is if we understand uncertainty, we can then try to come up with something that's robust, and maybe it'll match the biology. I'm not sure.
Thanks, Michael. So our next question, I believe, comes from YouTube. We've got impact invariant velocities are interesting. One, is this a matter of control or state estimation? And two, by acting on this subspace, do you have a sense of what capabilities are lost? For example, active energy dissipation?
It's a good question. So I think is it a matter of control or estimation? I think there's a couple problems, right? One is the estimation. It's really hard to measure, velocities during these impact events. So I think that's one problem. I think the other problem is that the model is wrong. So you came up with this plan based on a rigid body model. The model is wrong, and it's wrong in ways that are kind of hard to predict. And so our sort of philosophy right now is to try to not predict them, but also try to not react to things that are going to be perturbed by the unknown model. As far as what capabilities are lost, I don't know of a great way to quantify that. I mean, we sort of still can dissipate energy, right? Which is not energy in the directions that can be impacted by force. One observation we've made, though, is that a lot of the motion, is in the non-impact invariant space, right? Like particularly for landing, right? You really are slamming into the ground. So if you look at sort of the velocities, the scale of the velocities, right? The scale of the velocity, the drug velocities is sort of much higher than these projections. So once you form the projection, you're actually left with relatively small numbers in general. What that means as far as what capabilities are lost, I think we still don't quite know, but it's a good question.
Excellent. So we have one question in the chat that I think we'll take offline. We have two in the chat now that I think we'll take offline, and a few hands that we're unfortunately unable to get to due to time. So at this point, I'd like to thank Michael for his talk, and we're going to transition to our next speaker.
Okay, great. Let me
So,
try share screen.
So our next talk is from Xiaoming Xie. Xiaoming is joining us from the University of British Columbia, where he's completing his PhD. And he's going to be telling us about some collaborative work with NVIDIA to get quadruped robots to traverse all sorts of wild terrains.
Thanks. Let me see. So the video window is getting in the way. Okay, great. Okay, so hello, I'm Jiaming from UBC, and this is a collaboration with Dennis from NVIDIA, and I will be talking about using reinforcement learning to control quadrupedal robots. Okay, let's move on. So just to make sure we are on the same page, so first let me just briefly tell you what does it mean to use reinforcement learning for locomotion control. So the goal of reinforcement learning is to train a policy, pi here, usually represented by some parameters theta. In this case, in our case, it's just a feed-forward neural network. And this policy pi will take the state of the environment as input. So the state of the environment can be the state of your robot. And if you have some perception sensor in your robot, then it can also be the terrain around the robot that's estimated from your sensor. And then based on this state, the policy will output an action for your robot to execute in the environment. And the environment will change based on this action. Also, the environment will provide a reward to the policy so that the policy can get a notion of how well it does in this, so how good or bad this action is. And so the policy will then update itself based on this interaction. And the goal of reinforcement learning is to optimize your policy so that the sum of reward over some time horizon will be maximized. Okay. So first part of my talk would be about how to improve the speed of reinforcement learning with a GPU-based simulator. And so the limitation of reinforcement learning is that it's slow. So on this figure, we have see a usual pipeline when you are trying to use reinforcement learning to control a robot. So usually because the large number of interaction that is required between the robot and the environment, so it's typically infeasible to train your policy directly using your real robot. So usually we will build a simulation of your robot and use that simulation to interact with a simulated environment. And those simulations usually is implemented on the CPU. So depends on how many CPU core you have, then you can only run a limited amount of simulation, and then the data collection can be pretty slow. And then once you run your simulation step, then you need to calculate the reward, and also you need to calculate the state that you want your policy to see, etc. And also this usually will be computed in the CPU. And then because we are optimizing for a neural network, the most efficient way to train a neural network is to optimize it on the GPU. So you need to pass all this data from CPU to GPU. And this introduces a bottleneck because of the data transfer between the two different processors. And so again, to sum up, the AI is slow because the simulation on CPU causes some limit on how fast you can collect your data, and then also the bottleneck between CPU, GPU data transfer. Okay, so what we introduce here will be to put everything on the GPU so that first the data transfer overhead between CPU and GPU is eliminated. And then because now we can run the simulation on GPU, and GPU is specifically designed to parallelize parallelized computation. So now you can easily run hundreds or thousands of simulations on a single GPU. And if you are trying to do that on CPU, then you typically will require like by 100 or 1,000 CPU core, which can be expensive. And so this is what we call Isaac in NVIDIA, and there's a preview release. So if you're doing locomotion control for doing reinforcement learning for locomotion control, then I strongly recommend you to try this out. And so just give you a sneak peek of what it looks like. So here we are simulating 1,000 Locogo robot on GPU in real time. And typically the time that's usually required to train a capable policy usually requires days or hours. Now we can just train this policy in 30 minutes because of an efficient pipeline. Okay, great. Next, I will briefly tell you about how we do control for our quadruped. So it's a combination between reinforcement learning and model-based control. So again, some background on a model-based controller that we implemented on our robot. So we'll try to control this quadruped robot called Locogo. And first we make assumption that the context sequence is pre-specified by some users. So either the robot is doing trotting, pacing, or walking. So at each moment in time, you will know which set of legs are in contact with the ground and which set of legs are in swing phase. And then this allows us to divide the control into stance foot control and swing foot control. Okay, so for the stance foot control, we have the state of the robot body as input. So the state of the robot body is just means the linear position, linear velocity, orientation, and angular velocity of the main body. And then we have some desired body state that's coming from some user command. For example, you want the robot to walk at some certain speed, forward or backward, etc. And then this will go into a body PD controller and give us the output of the PD controller will be a desired body acceleration. But because the robot is under-actuated, we cannot just apply any body acceleration as we want. So this will go into a QB solver, which will generate a set of ground reaction forces for the stance foot, so that the ground reaction forces will produce the acceleration that's as close to the desired acceleration as possible. Okay, for the swing foot control, again, we have the body state as input to the foot placement strategy. In this case, it's just a simple Reber heuristic. And so this will give us a foot target position. And then we will generate a curve that connects the foot target position with the current foot position. And we will just implement a simple position controller to generate a swing foot forces to check this curve. And then these foot forces will be converted to joint torques using Jacobian transpose. So you'll notice here that there's no learning happening anywhere here, but we propose that we can replace some of the components to learning components so that we can get more efficient performance for our policy. So for example, we can replace the PD controller with a learn component so that we do not need to tune the PD game ourselves. We definitely can do better than just simple Reber heuristic for our foot placement. And also the context sequence is pre-specified, but sometimes you don't want to pre-specify your consequence because in different scenario you want different gates for your robot. So just to give you a rough comparison of performance of different controller that we try out. So the heuristic here just means the controller that we just described without any of the learning components. So here, they just run a PD controller for your stance foot control and then Reber heuristic for your swing foot placement. And you can see with some decent tuning, we can get it to walk across a nice hilly terrain easily. So that demonstrates our baseline is pretty strong. However, when we put it on the more complicated terrain, like the stepping stone terrain, where the robot also need to avoid a gap, then the PD controller, so no matter how we try to tune our PD controller, it just cannot generate stable command for our robot. So next, we try to replace the PD controller with a learn component. So we use a learn policy to generate the body acceleration command. You can see it can now easily traverse the terrain without problem. So we hypothesize it because the PD controller is just look one step ahead, while a reinforcement learning policy will try to look further ahead so that it will try to generate more stable command in anticipation of what will happen in the future. But it also has its limitation. So because we pre-specify the context sequence, so it's always doing this trotting gait, no matter what kind of command that we use. So for example, when we command the robot to just locomote at 0 speed, the optimal way in the sense of saving energy would be to use the standing gait, but because in this situation, we just use a trotting gait, so we just keep trotting anyway. So the next, we also introduce learning context sequence into our framework. Now at 0 speed, if we just use the standing gait, and then we command it to walk forward. And then now when we command it to stay still, then it will just use the standing gait. So pretty cool. And finally, we also learn a policy to ask the robot to traverse this large gap scenario where a trotting controller will have some difficulty to deal with that. While in this case, we learn the context sequence, so it kind of generate a galloping gait, I guess. So now as we introduce more and more learning components into our framework, our policy just get better and better. And it's currently a work in progress to learn also the foot target position instead of the Reber heuristic that we used. And hopefully that will give us the best performance for our policy. Okay, so lastly, we'll just show you some sim-to-real results for putting some of the policies on the real robot. So on the left, we have the robot running a policy that generates body acceleration command, and it can deal with unstructured terrain. On the right, we have a policy that learns the context sequence to drive this skateboard. Yeah, that's all. Thank you, and I'm happy to take questions. Okay. So now we just
Thank you very much, Xiaoming. Very exciting. So I don't think we have any questions. We'll wait for a minute for them to come in via the chat.
Yep.
I guess while we're waiting for those, I have one question to get us started. So you had mentioned that the PD controller is essentially only looking one step ahead. Can you comment on layering your learning on top of this PD control strategy as opposed to layering it on top of perhaps a more predictive control strategy?
Yeah, sure. So the benefit of using just a PD control, just using a one-step controller is that in this QP solver, if we are doing a model predictive control strategy, then either you are solving a nonlinear control problem, in which case you need some, you're doing some nonlinear optimization instead of this QP solve. But while if we are just using one step look ahead, then we can just use the linearized dynamics at that time instance and use a QP solve, simple QP solver. And this allows us to efficiently compute the control input at current time step in real time. But because we are doing reinforcement learning, the reinforcement learning policy during training see all the possible outcomes that will happen, and then it will make control. Even though the control command only apply at the current time step, but because of the control command is coming from a reinforcement learning policy, it's able to look further ahead instead of just a simple one step look ahead. That's the answer question. So it's a more efficient way to use compared to a MPC solver, which will require you either to linearize. So you have either you have a reference trajectory over time and then you linearize it, or you solve a non-linear control problem, non-linear optimization problem, which can take a lot of time. So it's not real time anymore.
Sounds like so your learning is more efficient as a result.
So it caches all the computation offline because it still takes a lot of time to train it. But when you deploy on the robot, you just solve this one step ahead problem.
Thanks. So we've got a couple in here. Is there any further learning for the sim to real part, or do you just employ the learn sim policy on the robot?
Yes, we just apply the learn policy without any tuning.
That's exciting. Another question here. In learning the contact mode sequence, does the policy choose from a fixed set of gates, or can it also generate non-periodic contact sequences? If the latter, how does it handle sudden transitions in contact modes?
Okay, let me see. So the okay, now just get out of the presentation mode. Okay, so yes, so we tried both approach. So for the video here on the right, we just choose from a fixed set of contact sequence to train this policy. But recently, we also tried to instead getting away from just learning a fixed fixed set of gates. And so what we do is we define a phase variable that's running from, let's say, 0 to 2 pi. So when the phase is from between 0 and pi, then the foot is in stance phase. When it's between pi and 2 pi, then it's in swing phase. Swing phase. And then when it gets to 2 pi, it just reset to 0. And then we are learning the speed of this phase variable so that it can increase at linear speed from 0 to 2 pi, or it can go at non-linear speed from 0 to 2 pi, depends on the task. So what we show previously, okay, let's just get out of the, unfortunately, the PowerPoint doesn't.
I think that's a great answer. Thank you.
Okay, great.
We've got a hand raised from Andy.
Yes, I had trouble following the details of the actual policy you learned. The policies are mapped from state to control actions.
Yes.
How much And you described the state in terms of body posture, but presumably the state also includes something about the ground. How much ground information is in your state that's in your policy?
Currently, for the ground, so we just use so because we are not learning the foot position, so the swing foot target for our policy yet. So currently the policy doesn't know what the ground looks like. It's entirely make decision based on the swing foot target position. So it knows where the swing foot want to end up. So it kind of know the ground indirectly, but it doesn't. The ground is not an input to the policy yet. But if we want to learn the foot contact position, foot target position for the swing foot, then we will need the terrain information into our policy.
Right. So something, thinking about bipeds, you're sort of using something about the intrinsic stability of the quadruped, perhaps.
Yeah.
So because you don't have your thing works with any foot placement, it seems like. Right.
Yes.
You know the foot placement and it deals with it. Okay.
Very good. We've got one question here from YouTube. I think our last one for this talk. Do the foot landing positions represent discrete foot placements, or is there a continuous space within each post type, within each position, perhaps?
Okay.
In a sense, is it handling an integer or a mixed integer problem?
For the foot placement, so on the continuous terrain, it can place the foot wherever we want in the XY plane. For the stepping stone scenario, we are discretizing the terrain so that we can, and then so we choose some specific, so there are a set of specific points the robot can put its foot on. So it's a mix between continuous and discrete choices. Yeah.
Very good. Thank you very much for sharing your work.
Yep, thank you.
Thanks for coming again.
Okay.
All right. So we have our last speaker for the session, Dr. Dai Awaki. Dr. Awaki is going to help us transition to our second set of talks by addressing aspects of both robotics and biology, talking about interlimb coordination, considering both neuronal feedback and physical feedback in terms of how the body interacts with the environment.
Can you see my slide?
Very good.
Okay. So thank you for kind introduction. I'm Dai Owaki from Tohoku University, Japan. So now in Japan, I'm on the 3 a.m. So my wife and son is sleeping now, but I'll do my best. It's my first time this kind of midnight presentation. Anyway, today I'd like to present our research entitled Robotic and Biological Interlimb Coordination. The summary of my presentation is shown on this slide. Our main research interest is interlimb coordination control that enables adaptive animal locomotion. And we consider that local sensory feedback to the neural control system is key to understand the interlimb coordination mechanism. So today I'd like to share the results about robotic interlimb coordination in quadruped and hexapod locomotion in the first part. And I'd like to talk about biological interlimb coordination in the cricket locomotion in the second part. Before start the main presentation, I'll review my history in this dynamic walking conference. 2009 was my first time to join this conference at Simon Fraser University. In this conference, I presented passive dynamic running machine, like these movies. And this year, I've just got my PhD, and it was so fantastic time for me. And after that, I joined this conference. Sometime I present our quadruped locomotion work in this conference. This is the first part of my today's presentation. And after that, a part of my research interests has shifted to the insect locomotion from robotics to biology. So the second part of my presentation focusing on the cricket locomotion. Of course, I'm originally engineer roboticist, so another part of my research topic is application of robotics technology for walking rehabilitation. So if I have a chance, I'd like to share the rehabilitation research in this conference in future. So about the related topic of today's presentation, we now organizing the research topic on the frontiers with Professor Manon Pong from University of Southern Denmark and Professor Ayari from Tel Aviv University. We already have 18 accepted papers. The review process have already finished. But if you are interested in this topic, please visit our site and refer our paper. We have many interesting papers about related to the biological and robotic interim coordination. Anyway, I go back to my presentation. So animals exhibit adaptive locomotion not only to environmental changes, but also morphological changes. This movie shows cricket locomotion in various situations. The left top movie shows intact walking on the ground. The cricket exhibits tripod gait, as with other insects. When we put the cricket in the water, like this movie, they can swim with breaststroke or swimming gait. So interestingly, they can immediately and adaptively modify leg coordination according to the environmental changes. And the lower figure shows a leg amputation experiment. Surprisingly, even after drastic morphological changes, a cricket continued to walk and show a gait pattern that depends on the number of legs remaining. For example, left movie shows a 4-legged cricket and right movie shows a 3-legged cricket. And I'm really impressed by this kind of amazing adaptive function. And I'd like to illustrate the leg coordination mechanism and implement it into the robot control. This is my basic motivation of this research. So the first part, I will introduce our robotics research, mainly focusing on quadruped locomotion. So as you know, quadruped exhibit versatile gait pattern according to environmental changes, animal species, and locomotion speed. And biological experiment involving this celebrated cat have suggested that their locomotive pattern are controlled in part by distributed neural network called central pattern generator CPGs in spinal cord. In our research, we propose a load-based interim coordination rule described by the phase oscillator model as a CPG shown here. And I'll explain the model in later slide. And then we have reproduced the various gait pattern in quadruped animal by using minimal and simple structured quadruped robot we call the Ostrex. So this movie shows a representative result. In this experiment, we changed only one parameter about the intrinsic angular velocity of oscillators. And by only changing the parameter related to the locomotion speed, the robot exhibits spontaneous gait transition from walk to trot to gallop without any predefined gait pattern. Again, the point of our research is that we did not use any interlimb neural connection between legs controllers. So I'll explain the model briefly. So for the generation of basic leg movement, we use a phase oscillator in which, according to the oscillator phase, leg is controlled to be swing phase for 0 to pi, and to be a stance phase for pi to 2 pi, as shown in this figure by using the crank mechanism. And the term of local sensory feedback describe this equation, where sigma is sensory feedback is described by the where the sigma is feedback gain and Ni is the load sense information detected by pressure sensor on the robot foot, and cosine phi I is a function of the phase phi I. The point is that in this equation, we use only suffix I. It means this model is totally decentralized control. So according to this feedback function, if ni greater than 0, phase is modulated toward this point, 3 pi over 2, like this. This meaning the mid-stance phase. So, and this physical meaning of feedback term is that while leg supporting the body, as this figures, leg remain the stance phase. This is important meaning of this feedback. Again, leg remain the stance phase while supporting the body. So this slide, I'll explain how interim coordination is achieved using this CPZ model. So here we consider the case when the left foreleg enters the swing phase like this. In this case, the left hind leg supports the body at the end of its stance phase, and phase delay is introduced depending on the magnitude of Ni. Here, this front leg enters the swing phase. The load on this hind leg is increased like this, and this phase delay allows time for the left foreleg to enter the stance phase again like this, and begin to support the body. The effect causes the center of mass of the body move forward like this. In turn, the load of the left hind leg decrease like this. As a result, phase delay effect on the left hind leg decrease depend on this term. It's allow left hind legs to enter the swing phase like this. Note that Ni include the information regarding the physical situation of the other leg at that time. This is important point, and which enables the model to fully exploit physical communication between leg movement without direct coupling between oscillator, unlike the most previous CPZ models that exploit interim neural connections. And based on the similar load-dependent interim coordination, we have reproduced various kind of insect-like hexapod locomotion in the robot as shown here. If you're interested in, please see our papers. So we have successfully produced various aspects of interim coordination in animal locomotion by focusing on minimal and simple mechanisms. But it cannot, of course, it cannot explain all aspects of animal behavior. And some limitation is that the mechanical and neurological structure, motor, sensor, organ are totally different between robots and animal in this situation, depending on the technological limitations. Our robot is always facing this kind of higher gap between the robots and animals. So this is one reason why my interest is shifted to the analysis of actual insect locomotion. So next part, I'd like to introduce the biological interim coordination in the cricket. So for the evaluation of leg coordination pattern of the cricket walking before and after leg amputations, electrophysiological experiments were performed with simultaneous recording of changes in the EMG of middle leg muscle and leg movement during the walking by using self-developed measurement system like this. And here we have chosen the levator muscle, number 96, as shown here. This is because it is the easiest to measure EMG signal during the walking because it locates on the coxa. So we analyze changes in relative muscle activation timing between levators of middle legs. In these four conditions, this cross point represents the amputation point of the leg. So in this case, we amputated the leg at the FTI joint. In this case, we cut the leg at the CTR joint. To calculate phase relationship between the muscle activation, we conduct the cross-spectrum analysis. And this figure shows the phase relationship of the leg muscle activation between left middle and right middle levator in these conditions using the circular histogram plot. The bold line represents average phase and the length, its length represents the standard deviation over all trials. The color represent indices representative of degrees of in-phase and anti-phase synchronization. Red color represent anti-phase. It's because this around pi radian, and the blue color represent in-phase synchronization because here is 0 radian. So this right panel shows the average phase and standard deviation over these 4 conditions, A, B, C, D. And these results indicate that the timing of muscle activation between the left and the middle leg are modulated from anti-phase to in-phase synchronization through this experiment. So we found that the activation timing of levator muscle in both middle legs tend to synchronize in phase when both legs were amputated at CTR joint. And some crayfish, lobster, shrimp use the swimmerlet, which are paired amputage on each segment of abdomen to swim. So the movement of swimmerlet has been found to be contralateral in-phase synchronization pattern like this figure. And from the movie, cricket pressed on the surface of the water exhibit breaststroke-like swimming gait in which the left and right legs move in phase like this. So these previous studies suggested that existence of intrinsic contralateral connection with ganglia that coordinate in-phase contralateral movement pattern. And of course, sensory feedback plays an essential role in leg coordination during insect locomotion. So the 4 conditions of our experiment represent a spectrum of reduced effect of load sensing information from campaniform sensilla on leg coordination. For the condition with anti-phase synchronization reflecting the great effect of sensory feedback, and in-phase synchronization reflecting the least effect of the sensory feedback. So suggesting that sensory feedback from mechanoreceptive campaniform sensilla overrides centrally generated coordinated pattern of CPG, leading to normal walking gait pattern of the insect. These findings is consistent with our previous robotic study in which we proposed load-dependent leg coordination rule that exploits local sensory information for each legs. So that's a summary of my presentation. And a future direction, recently robotics-inspired biology has been proposed for understanding the mechanism of animal behavior. Following this trend toward tight collaboration between robotics and biology, we propose a method so-called motion hacking for understanding locomotion mechanisms by controlling animals. The motion hacking is a method, external and precise engineering method of interference with neural motion control based on electrical stimulation of leg muscle, while retaining the insect's own sensory motor functions. So we observe, by using this method, we observe the leg coordination process by the insect's own nervous system when the leg is controlled externally. So please look forward to the future progress of our research. That's all for today's presentation. Thank you for your attention.
Thank you very much, Dr. Iwaki. So while we're waiting for perhaps our first question to come in, I have one myself. So the strategy of using the force measurements to modulate the gait phase.
Yeah.
You have a sense in biological systems how much of the interlimb coordination might come from physical or passive communication versus more neuronal communication, and how we might even quantify that if not?
So I guess in the biological system, of course, biological system has intrinsic neural circuit that makes the basic coordination pattern. But for adapting the environmental changes or morphological changes, in that case, animal exploit the sensory information from some sensory organ in the body. This is our hypothesis.
Okay. So we've got a couple of questions here in our Zoom chat. One from Edgar Bolivar. To my understanding, the rate of change of the oscillator depends on the load of the leg. what happens when the load changes due to different terrain conditions, for example, slope or uneven terrain, instead of the case of locomotion on level ground?
Do we have you, Dai? Are you on mute? Oh, yeah, there. Yeah.
Ah, okay. Sorry, so I'm thinking. Sorry.
Okay.
So, yes. So in the case, the load change due to the differential condition.
In a sense, does your oscillator synchronization strategy also work when you're considering locomotion on uneven terrain?
Yes, but in our model, this is a simple first one. So it can only detect the direct force directed to the leg axis. And in this model, it cannot detect the, for example, the perpendicular to the leg direction. So if, for example, the friction is changes environment in friction is environment that changes the friction, this model cannot adapt that kind of situation. So, but if we put another feedback term that can detect the perpendicular direction of the leg and add another model to coordinate that environmental change, it would be possible to adapt that kind of environmental change.
Very good. Thank you for the answer. One quick question. This will be our last one. Your work implies that mechanosensory feedback modulates the animal's gait. Could you suppress mechanosensory feedback, for example, by chemicals or cutting sensory feedback paths in your experiments?
In my experiment, just amputated the leg. Yes, in my experiment, just amputated the leg.
I think what Alex is getting at is, in order to test the hypothesis that this force feedback might play a role in animals, could you try to suppress that feedback in your experiments rather than looking at amputation?
Yes, and so for example, we consider the experiment for next step by adding the, for example, like prosthetic leg after the leg amputation. So that kind of prosthetic leg cannot detect any sensory information. So in that kind of experiment, we can check which sensory information is important for the leg coordination.
We'll look forward to seeing it down the road.
Yeah.
All right. With that, let's thank Dr. Iwaki again for his great work.
Thank you very much.
And I will hand the baton back to Christian.
Well, thank you so much, first off, Patrick, thank you for doing a great job of moderating our sessions and keeping us on track here and for moderating everything. So thank you very much. Let's applaud Patrick for keeping everything, all the trains running on time. Well done. And also want to thank all of our speakers in this session. Wonderful stuff. I have to give a little special nod to Dr. Iwaki, who it is 3 a.m. right now. So please, an extra thank you. We are so thankful that you could be here at 3 in the morning. So I'm very excited. So our next session coming up, we are pretty much on time. We're going to push back about 5 minutes. So we're going to reconvene at 2:45. The spatial chat is reposted in the chat room, so you can see where it is. We will reconvene at 2:45. So I'll see you all then. To everyone on YouTube, we'll be back in about 10 minutes. All right. We will begin our session about 2 minutes or so. We'll start getting ramped up. So Helen, let me make sure that you are a co-host. Fantastic. Hello, Katie. It's good to see you.
You too.
Glad to have you.
Thank you.
So you should be now a co-host to the meeting and should be ready to share screen whenever you're ready. Could you confirm that you have a share screen option available for you?
Yes, I do.
Fantastic. All right. Do you want to try that before we get started? Or
Sure.
are you all set to go? Okay, go right ahead, just to make sure.
Look good?
Looks great. It looks like a slide and a very crisp one at that. So,
Perfect. Thank you.
of course. All right. So according to my timer, we'll be active in about 30 seconds. So, okay. And welcome back, everyone. It's great to have you back for our second session of our control episode of Dynamic Walking 2021. In particular, this is our biomechanics focused session, and I couldn't be more happy to introduce Dr. Helen J. Huang from University of Central Florida. She's an assistant professor who specializes in multimodal neuromechanics, EEG, all in human locomotion. So Helen, feel free to take it away.
All right, great. Thanks, Christian. Welcome to the biomechanics talks of the neural control episode of Dynamic Walking. We'll just get started. Our first speaker is Dr. Katie Poggency, who earned her PhD from Stanford earlier this year. Her talk will focus on the human in the loop optimization.
Okay. Thank you very much, Helen. As Helen said, I'm Katie, and I'll be focusing on the human in the human exoskeleton system. So it goes without saying in this crowd that exoskeletons have the potential to improve mobility. By providing assistance to joints during walking, you can reduce the amount of work that the person has to do to maintain a steady gait. Let me double check this. And so this can make walking easier for people with neurological disorders or people who have to walk long distances or carry heavy loads, which can then improve quality of life and just make people happier in general, as seen here. So as a field, we've made massive strides in exoskeleton design, starting with a concept in the late 1800s and progressing to today, where we can reduce the energy cost of locomotion using a wide variety of exoskeletons. And these devices all work really well, but I would argue that the next big step in exoskeleton development is to address the missing part of these pictures, the human. So there are a couple of ways to use human performance to improve device implementation. And the first is to train controllers based on human performance. And the second is to train people to better use the devices. As a lab, we've previously presented work at Dynamic Walking about human in the loop optimization. So my talk today will just focus on the training and motor adaptation aspect with some insights into how people respond to customized controllers produced through human in the loop optimization. So how do these factors affect human exoskeleton performance? To test this question, we designed a 6-day experiment with novice users using bilateral ankle exoskeletons that act in plantar flexion. So these participants began with a pretest where they walked in normal running shoes in unpowered zero torque mode and with generic assistance. This generic profile was the average optimized profile from a previous human in the loop optimization experiment. For the 5 subsequent days of the experiment, participants started with a 74-minute adaptation trial, followed by more of those 6-minute validation trials, testing those same baseline conditions, and also the generic assistance profile. This allowed us to track how people learned how to use the device by testing them every day. Participants were randomly assigned to one of 3 training groups. The continued optimization group experienced optimization throughout adaptation, starting each day where they left off on the previous day. And this resulted in large variation at the beginning before tapering to less. The static group experienced the same profile for the entire trial, so they had no variation in training. And then the reoptimization group experienced the same optimization as the first group, but it was reset each day. So the average variation remained high. 2 of those groups, as I said, experienced human in the loop optimization. So a quick overview of that. You take a set of candidate parameters, all sampled near your best guess, as you do with any optimization algorithm. You can then apply those parameters to the person and measure their performance. Here we used metabolic cost, but you can use any sort of objective function you want. You could use muscle activity or preference or anything like that. Once you've tried all of these different controllers, you can then rank them, and that will give you a new best guess. So this loop is what we call 1 generation of optimization, and typically we do 4 generations, which is about an hour of continuous walking. The parameters that we chose defined a stride-based ankle torque control profile. Those parameters are peak time, so the time to reach the peak magnitude, rise time, the time from the onset of torque to that peak time, fall time, the opposite, and peak torque magnitude. So these 4 parameters can produce a wide variety of control patterns, as shown on the right. As I said, these 2 groups experience human in the loop optimization, which then yields a custom optimized profile. That's tested alongside the other validation trials. And so at the end of 5 days, the continued optimization group has a profile that is a result of 20 generations of optimization compared to the reoptimization group, which is just the result of 4 generations. So we can look at how these factors affect metabolic cost. And initially in the pretest, which accounts for 12 lifetime minutes of assisted walking, we see a slight improvement in energy economy with assistance. This 10% reduction compared to zero torque is on par with what we see in some of those early exoskeletons. However, after several days of training, participants are able to triple the energy savings with the same assistance profile to over 30% compared to the unpowered condition. The static training group did just as well, and the reoptimization group improved, but not to the same extent as the other 2 training groups. This suggests that the type of training may have led to a different type of gait. Because there was more variation, potentially these participants adapted to a more robust gait that is robust to lots of variation, but possibly not as effective at using that generic pattern. While there's a lot of variation in how people responded to the assistance, we found that overall adaptation took a really long time. Previous training studies, of which some of the authors will be presenting later, settled on training times from 90 minutes all the way down to 18. Here we defined expertise time as the time to reach within 5% of the asymptote. And so if you only walk for 18 minutes, you're within 22% of the asymptote, just for a sense of how long this takes. And we can look at how this changes across training protocol. Moderate variation appears to speed adaptation, with the continued optimization group converging in 130 minutes compared to nearly 220 minutes for the static training group. But if you remember from earlier, this does not necessarily result in better energy economy in the long term. We think that potentially the large variation at the beginning of optimization for the continued optimization group may have helped to speed the initial adaptation before tapering to a similar protocol to what the static training group experienced. The re-optimization group appeared to converge in less time, but as we said before, they may have learned a different coordination pattern. So this estimate of 2 hours that I keep talking about is not necessarily the number that you should attach to all exoskeleton studies. We think that this time is incredibly context dependent. This 2-hour estimate may be an overestimate for easier to learn devices like unilateral devices or devices that act in dorsiflexion, but we would expect that time to go up for more complex devices like multi-joint devices or complex conditions like uneven terrain. And we would also expect this to go up for people with movement disorders, which makes this all a lot more difficult because these are the people that we're trying to help, but people with movement disorders cannot necessarily walk for these long trials. So while it's great that we've shown the importance of training, this presents a whole new area of research that we would need to solve before bringing these devices to a wider population. So what I've shown so far is just the metabolic cost of generic assistance, but we did customize some of our profiles. And we found that customization led to even greater metabolic cost reductions with an added almost 10% bonus. But too much variation can impede adaptation. So this only holds if people are fully trained and the optimizer has enough time to find the optimal solution. So in general, training and customization of the control parameters improves metabolic cost reduction. And too much variation in training can impede training, but people are still able to learn just as effectively by walking in a static profile for just as long. And metabolic cost is a very important measure of performance, but as I'm sure we'll hear all about in the next episode, it's not the only measure. So we can look at how the exoskeleton control changes throughout the optimization and how all of these different factors can affect exoskeleton performance. We discovered a few features in the optimized profiles. The first is that intersubject variability seen in metabolic cost could be the result of variation in the customized parameters, particularly if you look at the magnitude of the torque that varies between the different participants shown in different colors on the right, and the onset time. So you can see that the olive is a little bit later. We're not entirely sure how much intersubject variation makes a difference in optimized parameters. So for more on that, go chat with Gwen during the poster session in room 3. But if customization is not the most important aspect, we can look at how the customized profiles differ from the generic profile to see why people did better with those. So we can see that the profiles are larger in torque magnitude on the left, and the customized profiles were also characterized by larger mechanical power. So on the right, you can see that the customized profiles represented by the triangles are further to the right or exhibit higher power than the generic profiles shown in the circles. Optimization appeared to occur over different time scales. These 4 parameters were free to optimize over different time scales, which they did. We found that peak time converged quickly and reliably to late instance. Rise time and fall time converged quickly, but less predictably. So rise time might be subject specific, but it might not be. We need to do a parameter sweep to fully gauge how important that parameter is. Fall time appears to be determined by late peak time. So because the peak time was late instance, we required that the toe off or that offset time occurs around toe off, which is why that fall time kind of fluctuated. Magnitude steadily increased, which indicates more time to converge. The average was 0.68 Newton meters per kilogram, but the asymptote is 1. So there may be neuromuscular changes, or which may be the result of increasing strength or changes in the distribution of slow twitch and fast twitch fibers, which means we may need more training time or more targeted training. My time is almost done, but one more slide about the mechanical power of these devices. So power is a very complex story that I'd be happy to talk more about. In our case, because we have a torque profile, people can alter their kinematics to alter the amount of work they receive from the device. So if you just look at the generic assistance profile, which is a fixed profile for everyone, people appear to adapt their kinematics in ways to reduce the amount of mechanical power they receive from the device. So there's this idea that the more power that you inject into the system, the larger the metabolic reductions. So it appears that the story is more complicated, and in our case, as people reduce their energy costs, they also reduce their mechanical power. So in summary, people can successfully use generic or customized assistants, although customization appears to provide greater benefits. And we also found that the length and type of training matters. So just in general, people are really complicated, and you always have to consider the human in the human exoskeleton system. So thank you.
All right, thanks so much for a great talk. Let's get some questions in the chat. We have one in the chat from Greg Sawicki. If you knew the torque profile early in adaptation, can you predict the final optimal profile at steady state?
That is a good question. We can potentially estimate for this specific paradigm and these participants based on those the optimization trajectories that I showed. But there's no guarantee that it would hold for if you were to use a different device or a different group of people. We looked into if there are any inter-subject characteristics that may predict what the final optimized profile is. And short story, we didn't really find anything. We looked into psychological measures like grit or dexterity, and people are hard to predict. So while we can find a profile that is probably good, it might not be the optimal.
All right, great. Let's take one of the hands raised question. Let's go to James Finley.
Hi, Katie. Can you pull up the figure where you showed the adaptation of the individual parameters a couple slides back?
The one that I just talked about without pulling up, that one, yes.
Yeah. So the most striking thing here to me is this peak magnitude that looks relatively linear, has not plateaued over 20 generations. And it strikes me that maybe people have a really hard time learning how to take advantage of large levels of assistance, right? So that's what they're working toward. It seems to be really effective when they can do it. What would you imagine would happen if you just did this from the beginning, right? With these really large peak magnitudes, I imagine that there could be some, maladaptive responses initially. What do you think would happen if, well, one, why do you think it takes so long to plateau? And two, what do you think would happen if you started with these really large magnitudes?
So I know that initially people would hate it, and we would probably get a lot of dropout. I worry that if we put too high of torque into the system initially, people might adapt to that robust kind of gait. So it may actually take longer to unlearn that robust behavior and learn to take advantage of it. So the way that our optimization worked is we had 2-minute periods where we changed the controller every 2 minutes. We have not looked into more of those slowly evolving kind of trajectories. I know that Rachel Jackson a while ago did a heuristic-based controller where it changed on a step-to-step basis. And I think potentially if we were to give people those higher torques, but maybe build up to that over the course of like a few steps, that might be a little bit easier to learn. I don't have a good sense for what would happen to every person if we were to initially give them this kind of profile. I think the initial adaptation might be a subject-specific thing, but maybe they'd be able to use it and maybe our training times would be faster.
It'd be really interesting to explore. Thanks.
We got a few questions in the chat, but maybe time for one more. So this one piqued my interest. Do you know what people adapt in their biomechanics to adapt to the device over time? And if so, can we coach people vocally to adapt faster by telling them what to do?
Yes, we are looking into that. I have a whole set of slides that did not make the 12-minute cut. Kind of briefly, we found that kinematics didn't really change by the final day, but there may be changes over time that we could coach people towards. Sabrina Abram did a really nice exploration of this where people appear to increase their exploration. So their variability increases in a lot of different parameters, including muscle activity and step frequency and things like that. And then they appear to converge. So my first guess would be to coach people to explore the space. We know that forced exploration is really good. And then potentially train them into, some sort of ideal kinematics, which right now appears to be the same kinematics as their normal walking. But I think we just don't have enough data to really make any definitive statements on that.
Actually, I think we have time to squeeze in one more question. So from the chat, do you have insights how the learned exo profile compared to the subject's natural profile?
So for the torque magnitude.
Didn't specify, but let's say torque.
Okay, cool. I see a yes. So the torque magnitude is significantly lower. We saw that it was 0.68 Newton meters per kilogram. And the normal ankle torque magnitude is significantly higher, which was outside of the limit that we wanted to provide. We didn't want to provide anything over 1 Newton meter per kilogram. So it is the same shape. The parameters were chosen to define a similar shape, but the magnitude is lower.
All right. I guess let's move on so we stay on schedule. So what a great start to this session. Thanks, Katie. Now we'll transition to a talk by Dr. Amy Wu, an assistant professor at Queen's University. She'll be talking about controlling exoskeletons with neuromuscular models for balance and gait.
Can you hear me now? Yep. Okay, great. Thank you, Helen, for the introduction. So I think as Katie nicely introduced, exoskeletons are one really nice way to help with gait recovery, but there's a whole host of challenges and problems when trying to define, how do we control people and to interact with the exoskeleton and with the human. So some of the challenges could be what level of bioinspiration is needed from something that's simple to something that's complex. For instance, is it enough to just recreate kinematics, or do we need more of the dynamics part of it? Is the underlying basis of the model something like a simple inverted pendulum, or should we add muscles into it? And also, what active degrees of freedom are needed from a single joint like the hip, or do we need a full leg to actually help someone walk and recover? I think another challenging area, again, nicely touched upon by Katie also, is this idea of shared control. So this interaction between the machine and the device. So in some situations, it's probably nice if the machine will generate the gait for you. But in other cases, maybe when you have some sort of remaining function, and you want to do something like walk faster, some sort of interaction is better and maybe helps you to recover from gait faster as well. And finally, how do we evaluate how good an exoskeleton is, the efficacy of it? So metabolic cost, of course, is one measure, but as mentioned, it's really hard to put a patient population in a treadmill for a very long time and measure their metabolic costs. So some other measures could be what are their walking speed before and after, some training regime, maybe the muscular effort, or even some subjective measures like how happy they are or what their workload is. So, and of course, everything is also very intertwined, so nothing's independent from each other. So my talk will be in two parts. The first part, which I'll mainly focus on, is about the Symmetron exoskeleton project. And this is just going to be used as a case study to describe how we try to address these three challenges that I discussed here. And then looking into like ongoing and current work, we'll also talk about balance control for gait stability. So the controller we used for the exoskeleton project is a neuromuscular controller that was based on a reflex model by Hart-McGuire. And we used a sagittal plane model, so about 7 muscles per leg. The muscles have some dynamics, some hill type model, and the exoskeleton has sensors which will sense the joint angles. And this will give us the changes in muscle length. And through sensing these different changes in muscle length and forces, we will have muscle activations in our virtual model. And by combining the muscle forces across the muscles and across the joints, they become the joint torques, the commanded joint torques that the exoskeleton will use to actuate the exoskeleton. So we have very few sensors. Joint angles is one of them. The second is our contact sensors. So it's called a reflex model because it operates on stance and swing reflexes. So when the foot is on the ground, the stance reflexes activate. Doesn't want the leg to collapse, it's to bear weight. And if the foot is off the ground, we want it to be able to swing freely so it doesn't trip the person. So in simulation, the model has been really great. It can generate human-like walking dynamics. You can see the angles and torques across the hip, knee, and ankle joints, the muscle activations between model and human. So there's a lot of work that show that this model is really robust, not only for creating human walking and also for different perturbations and slope changes. So some of the benefits of this model are that it's a reactive controller, meaning you can modulate it based on your footfall patterns, so how long your foot's on the ground and off the ground. It also has decentralized modular control, meaning we can separate out the muscles into the different joints, and so you can apply that to different subjects or to different exoskeletons even. So it could be ankle-based or just ankle, hip, and knee, so any sort of control, you can separate that out. And also there's a sense of dynamics because there's these intrinsic properties from these virtual muscle models and these reflex loops. So it's not a static controller, it's actually quite dynamic. So I think all of these are kind of goes into the by inspiration, thing of by inspiration and shared control, because we have some inspiration from having these reflexes and these muscles and these dynamics, and also because of the reactive control, it's got some shared control between the exoskeleton and the human. So the objective of our experiment was to investigate the effects of the neuromuscular controller on the gait of subjects with spinal cord injury. And how we addressed the efficacy part of it, the performance, was that we looked at joint kinematics and torques. So looking at qualitatively in steady state. And then we tried to use the speed-step length relation as a proxy for energetic cost. So here I have the different muscle groups that were used in the sagittal plane model. And as we kind of alluded to earlier, you can apply these on different exoskeletons. So it could be just the ankle, so we take the soleus and tibialis anterior muscle. Lopez, which had the knee and hip power joints, so this is a gait trainer that's fixed. And then we had two other wearable exoskeletons where one is an ankle, knee, and hip. So it could apply, we applied it to all four of these. And today I'm going to talk about these two experiments. One thing to note, we didn't adjust for body mass, height, didn't make any sort of speed-related adjustments or reflex parameters. We kind of used the generic parameters from the model for this 80 kilogram person walking at 1.3 meters per second. What we did adjust was broadly the gain on the joints, like the knee gain, for example, could be scaled, but it's all to this generic number. So in a sense, it was like we had this complex control in a sense, but then when we apply it to subjects, we didn't do a lot of tuning to make it subject specific, just more broad tuning, and we'll see what happens. So the first experiment is the knee and hip gait trainer. So here we had people fixed. We had this sort of shadow legs, moving people's legs, and we put the neuromuscular controller on it. And we had people with complete injury that were walking in this exoskeleton controller. And so what we did here was we basically changed the treadmill speed from 0.8 meters per second to 1.1 meters per second. And we didn't, again, change any other parameters. We just had the treadmill walk. And then based on the footfall patterns, it created gait. And it was the first time we tried this on exoskeleton, so we actually had no idea what was going to happen. So it was pretty amazing that it was able to produce gait and to have something that looked healthy-like in a sense. So if we look at the kinematic and the torque data, so this I'm going to show you the angle and torque of the hip and knee. So this dashed or dotted black line is just a healthy subject. If you had a healthy subject walking the gait lab, what the profiles would look like. We also put a healthy subject in the gait trainer just to see what the gait trainer would do if we had someone healthy in there. And then the blue is someone with a spinal cord injury walking at 3 different speeds, from a slow to fast speed. And so things that kind of stood out for us is that the angles seem to work pretty well, seem to match healthy. angles, but then you have these different changes in torques that we weren't sure exactly showed up, and it didn't seem to actually affect the kinematics. So some of the takeaways from this experiment are we didn't impose any trajectories. Again, we didn't change anything, we just changed the treadmill speed. But we found that the joint kinematics were similar to healthy. We think the knee torque difference, so you see there's a lack of knee flexion. We think that's because of the lack of the ankle. So there's no powered ankle, and we didn't put in a gastrocnemius muscle because it's biarticular, so it wouldn't make sense. So that we think that's one reason why. And we're not quite sure about the hip differences. They're really deep hip flexion, but it seemed to have a small difference effect on the joint angles. So we wanted to not just look at a subset of strides, we wanted to look at the entire gait, and then it's really hard to apply what we could do with healthy subjects, such as measuring energetic cost, with a patient population because they can't walk as long as healthy humans can. So we thought about using the speed-step length relation as a sort of proxy for energetic effort. So here I show you the plot of speed and step length, where the gray area is the healthy region. So the step length is proportional to speed to some coefficient. So there's some sort of power law and the way we prefer to walk. And for healthy subjects, it's about, the coefficient is about 0.54. So if you were to deviate from this, then it would imply that you are using more energy because this is our preferred region that coincides with minimal cost. So if we put the strides from all these test pilots with a spinal cord injury onto it, we have all the data points that you see here. So one of the benefits is we can see all the data. And then we performed fits and compared it to the healthy region. So 4 out of the 5 subjects did exhibit some sort of power law in the sense that the coefficient was less than 1. So we did see that the power law emerged, but we did find, as you can also see in the figure, there are longer step lengths at faster speeds. So it kind of fell out of the region when we walked faster. And we think perhaps the longer step lengths could be due to body weight support. So we did have body weight support for these subjects, and maybe that encouraged them to walk with longer strides, and that could contribute to why they had longer step lengths at faster speeds. So what we did next was we moved from a gait trainer to a wearable exoskeleton. And one of the challenges is now that you're moving from treadmill to overground. So before we could test subjects with complete injury, and now this is a subject with an incomplete injury. So they do have control of their hip. And so here's a video of a subject walking. And I'm just going to show the speed step length data. So what I have here is, again, that same speed step length. And because these subjects are test pilots, are ambulatory, we can compare how they walk with and without the exoskeleton. So here, this is one subject without the exoskeleton. And then this is the same subject now with the exoskeleton and the controller. So you can see there's a wide range of speed, and they actually walk on average faster. And then taking a second subject, this is without the exoskeleton, the green triangles. And then when we have put them in an exoskeleton, then now they have a wider range that they can walk at, and on average, they're also faster. And then we also perform fits. And again, we do see that so if we just compare the neuromuscular fits, there is a parallel, but then it's still predicted to be faster at faster speeds than what a healthy person would expect to have. So the controller permitted these speed variations. Just a reminder, we didn't change any gains related to speed. So we had one set of gains, and the subject just walked in it, and that's it. And it was just the footfall patterns that adjusted and changed, giving a measure of shared control in that sense. So it was really great to see this. Of course, there's many different limitations, like limited subject set, but it was nice to see how the by-inspiration part and shared control played into it. So some of the limitations, there, as I mentioned, many limitations in terms of number of subjects, but I think the two that stood out for me in all these experiments is that it was actually very difficult to achieve very slow speeds, about less than 0.5 meters per second. And if you notice in these pictures, there's always some sort of external support, like crutches or handles, that are needed for balance. And this really kind of set the stage for me thinking about kind of the next steps. How can we address what happens at slow speeds, and how can we do better in respect to balance? So the last part of my talk will be about some of the current and ongoing work on balance control for gait stability, where we're trying to investigate the underlying mechanisms for maintaining gait. So there are broadly the 3 different strategies. We can take a step, we can modulate center of pressure with our ankle, we can use our trunk to balance. And the key questions you want to know is, how do humans maintain balance during gait? What are the relations between these different strategies? How we can translate those principles to assist human balance or as controllers for robots. So we're looking beyond stepping strategy. So the convention is that stepping is preferred, and we do take a step if we need to. But we found situations where stepping is not preferred. So it's not utilized when people are subjected to this passive inverted pendulum perturbation. So when this perturbation does is it actually discourages you from taking wider step widths. And we found that people didn't use stepping to counter this lateral perturbation. They chose to reduce their center of mass motion instead to counter this perturbation. So stepping wasn't preferred in this case. And going back to talking about slow walking, when people walked slower and slower, their body moved more and more laterally. So we want to see what sort of compensation came from that. And here again, we found that people didn't adjust their step width in order to counter that. But we think maybe there's some compensation provided by the hip and ankle strategies to compensate for the body sway, increased body sway when you slow down. The other thing we're looking at more on the robotic side is looking at the reduced order models from the lean inverted pendulum plus 5 plus variable height, and we combine them together to see how the model would react in response to perturbations. I think what we're starting to find here is that sort of human-like behavior in the sense that when you have small push forces, the ankle dominates, and as you get pushed larger and larger, the hip and knee start to dominate for the larger push forces. So kind of similar to how humans will transition from an ankle strategy to a hip strategy. And so I think all that is great. I think a challenge would be is then how do we translate those to robots into lateral stability? So I just wanted to show this video as well. This was, I think some of you might recognize, it's like a version of the Rando robot. But we were trying to get some sort of lateral stability in there. And you can see it actually will do this for a good 5 minutes, which was pretty amazing. But I don't know, it's not really dynamic in a sense that it's not making forward progression, sort of waddling in place. So just using that as like a kind of food for thought to think, okay, we have this complex task of understanding how humans balance, and then we have to translate that to exoskeletons and robots. So to summarize, I talked about a neuromuscular controller that had inherent capability to adapt to subjects' walking dynamics. In the sense that by inspiration, it had muscles and reflexes. It had a measure shared control through the footfall patterns. And we looked at efficacy through the kinematics and through the steps length-speed relation, and everything, of course, is intertwined. So it had very few sensors, and we didn't do any prior tuning. It made healthy-like behavior, could give subject-specific assistance, could walk at multiple speeds, and we didn't do any sort of scaling of subject height to make the model work. And for the balance portion, I want you to take away that stepping is important, but we think it's not everything. So we're really excited to dive into is what role does the trunk play when stepping is limited, and when does it become very important? So I want to acknowledge the Simbatraw team for the exoskeleton work and the students in my lab for the great balance work and the funding sources below. Thank you.
Thanks, Amy. Really great talk. Take some questions quickly here in the chat. Amy, are you implicitly assuming here that the step length speed relationship with metabolic costs is unchanged when you add the exoskeleton?
Yeah, implicitly, yes. So I wouldn't say it's correct, right? It was just us trying to figure out a way to analyze all the data at once and trying to get a sense of could we get energetic effort. And I think some of it comes from, I think, being trained in where we, in gait studies with healthy humans, where we would do a standard gait experiment and then figure out all the things we can, depending on the research questions. So yeah, I think it's correct that implicitly it's implied, but I wouldn't know if, without testing, I wouldn't say necessarily true. But it was just something interesting to look at to see how close it would be, if it would be completely far off or very similar.
All right, a question from YouTube. Thanks for the great talk, Amy. I have a question about reflex control. were there any long-term benefits for the patient from using Lopus or another exoskeleton with reflex control?
So for the controller that we applied, so we had so this was a part of a big European project, and so we had people at the Santa Lucia Hospital that did more studies with the exoskeleton, where they actually had people train over a longer period of time with the exoskeleton. And so when they trained this test pilots, they found that the speed before and after the training in this was actually faster after, so that the subjects were able to walk faster, or the test pilots were able to walk faster after training with it. So I think that would be one of the long-term benefits that we saw from the training with the exoskeleton versus conventional training, which didn't show the same benefits. They also are experts in looking at other clinical measures, so they found that other clinical measures also seem to improve when they were comparing training with exoskeleton and with conventional training.
Okay, awesome. I guess the last question, which I think will nicely transition to the last speaker, is on gait stability. How do you define that, and what do you consider maximal stability?
That's such a hard question. And I think one of the things, what's challenging in this work is what is stability, right? There is no answer to it. And so, yeah, no, that's a really hard question. I think even permeates through, like, how do we evaluate humans, or even in simulation, is a simulation model walking 20 strides, is that enough as stability? So I don't have a good answer for that. We are looking at, what we're interested in, one of the studies we're doing now is looking at how people walk outside and how they use their different strategies. And so we're trying to tackle that in terms of, like, we have all these different gait measures. You know, there's variability, which is could be, like, increased variability could be more stable or less stable. There's, like, step width and these parameters. There's just so many things. So I don't have a good answer to that. So I think what we're starting with is looking at conventionally what people have used, understanding the limitations of them, and then trying to think if there's any other way to combine things in a way that gives us a better sense of stability. But it's a very difficult question. It's a great question, but it's difficult.
It's always interesting to hear people's different answers to that question. I also find it a hard question to answer. All right, thanks so much, Amy, on your great talk. All right, we're going to move to our last speaker for the biomechanics portion here. So Dr. Keith Gordon, an assistant professor at Northwestern, he's going to talk about how prior uncertainty impedes locomotor adaptation.
All right, thank you, Helen. Everyone hear me okay? See my slide? I'm excited. Okay, great. I'm excited to present some brand new research that two of my phenomenal grad students, Oju and Mary, have been conducting, aimed at understanding how we control walking in uncertain environments. Following neurologic injury, the locomotor balance skills addressed in gait training can be addressed, or can be classified into two major categories. The first skill is essentially controlling oneself. And this is really the development of an intuitive understanding of how to produce and modulate a coordinated stepping pattern. The skill is practiced by taking many, many steps in a consistent environment, like walking on a treadmill. And this form of balance control is most closely associated with the formation of an internal model that would allow the nervous system to relate a series of efferent commands with a resulting motion. The second skill is learning to manage uncertainty. The skill is important as it enables the production of stable walking patterns in the face of common real-world challenges. Typically, this type of practice involves reactive type training performed in a dynamic environment with a range of walking tasks. The control of uncertainty involves, it's broad, but involves learning how to modulate limb and whole body impedance and learning to react to feedback. We are particularly interested in how and when one should begin to incorporate uncertainty, right, this reactive type of practice, into a gait training intervention. This question is interesting to us because the control strategies used in uncertain environments may interact with the ability to form an internal model to control walking. So this interaction could play out in many ways. For example, consider a person with poor balance control who adopts a high impedance control strategy, right, making their body and limbs very stiff when walking in a highly uncertain environment, such as walking on irregular terrain. This impedance strategy should minimize kinematic variability and movement errors. However, its effect on forming an appropriate internal model for walking, which is also a goal of gait train intervention, is not known. A high impedance control strategy could accelerate motor learning by increasing the likelihood that actual movement errors occur close to the planned movement space, thus allowing individuals to better identify sources of errors. Or alternatively, impedance control strategy could impede motor learning by reducing kinematic variability, an important signal for error-based learning. Oops. Thus, we set out to explore this interaction and hypothesize that exposure to external uncertainty would impede locomotor adaptation to a consistent environment. To test this hypothesis, we had healthy young individuals perform a series of discrete goal-directed walking tasks. Participants started each trial from a static standing position, and after receiving an auditory cue, moved rapidly to a target 1.5 leg lengths ahead, so approximately 2 steps away. Each trial was complete once the individual had stopped moving with both feet in the end target. During each trial, participants always stepped first with their right foot. And in addition, participants wore a snug harness around their waist that was attached bilaterally to a cable-driven robot that was used to apply laterally directed forces of varying magnitude to the participant. And then finally, to ensure a consistent walking speed each trial, participants were given some visual feedback about their speed after each trial. Okay, we use the cable-driven robot to apply 2 types of forces during walking. First, to evaluate locomotor adaptation, all participants completed walking in a novel and consistent viscous force field. The force field was created by applying a lateral force proportional magnitude to the participant's forward walking velocity. The applied force field produced a peak lateral force of about 17% body weight at their peak forward walking velocities. Also, to introduce environmental uncertainty during some trials, individuals experienced only pseudo-random perturbations. These perturbations were lateral impulses that varied in magnitude, direction, duration, frequency, and onset time. Okay, so specifically, what did? We had 2 groups of participants, a control group and a group we called the perturbation group, and they performed the following tasks. First, participants performed 20 baseline walking trials in which no net force was applied to the participant, as can be seen in this video here, or if I play it. There's walking, starts in the begin target, ends in the start target, no forces applied. Next, the perturbation group only performed 30 walking trials in which they experienced pseudo-random perturbations. So in this video, which is going to play in a second. Okay, so in this video, the participant was experiencing, on this trial specifically, a moderate single impulse perturbation being applied to their left. And this was varying. This was not a fun task for the individuals, getting pushed around a lot. Okay, and then next, both groups performed 70 walking trials in the novel and consistent viscous force field. The viscous force field, as I mentioned earlier, was always applied to the participant's right. We evaluated walking during the 4 trials in the viscous force field, which we term the early field, being shown in this video. So a pretty strong pull to the right. We also evaluated walking during the last 4 trials in the viscous force field, termed the late field, being shown here. So still being pulled to the right, but a much smoother movement after 70 trials of practice. And finally, we evaluated walking during 3 catch trials that were interspersed within the viscous force field in which no forces were applied. And here's what this looks like. The catch trials were valuable for understanding that underlying control. Removing the forces really allowed us to see what the individual was planning. Of note, participants were never informed of the external field that they would experience before they began each trial. To quantify changes in the participants' walking trajectory each trial, we quantified what we called their center of mass sign deviations. So this is the signed area of the center of mass trajectory relative to a straight line path originating from the lateral center of mass position at first toe off and ending with a center of mass position at rest within the end target. Okay, let's take a look at what they actually did. First, we'll take a look at the early field, right? The first 4 trials in the consistent viscous force field. So shown here are the center of mass trajectories for a representative participant from the control group during a single baseline trial and the first trial in the viscous force field. Clearly, the center of mass trajectory here deviated to the right, the same direction as the applied force field when compared to the baseline trajectory. We see a similar center of mass trajectory during the early field when we observe the data from a representative participant from the perturbation group. Right, they're deviated in the same direction as the field. If we take a look at the group averages, we actually found that the center of mass deviation in the direction of the force field during early field was significantly larger in the group receiving the prior perturbations, or the perturbation group. Now, we were actually quite surprised by this, as we had assumed that the repeated exposure to the prior pseudo-random perturbations would lead to the adaptation of control strategies that would increase resistance to all external lateral perturbations when compared to the control group. Okay, here we can take a look at how individuals performed in the late field, the last 4 trials of the consistent viscous force field. So as being shown here, we have, again, a representative participant from the control group. You can see that the center mass trajectory during the late field has returned to a trajectory that is very similar to the trajectory during baseline walking. When we compare this to the control, when we compare the control participant to a representative participant from the perturbation group, we can observe that the center mass trajectory did not return to a trajectory similar to baseline. An examination of the group averages confirmed what we observed in the representative subjects. The perturbation group trajectory continued to deviate in the direction of the viscous force field, even after 70 trials of practice. So this sustained center mass deviation, even after substantial practice, indicates that exposure to environmental uncertainty in this experiment impeded locomotor adaptation of the perturbation group. Okay, lastly, let's take a look at the CATCH trials. All right, those trials in which the force field was unexpectedly removed. In the representative participant from the control group, the center of mass trajectory during the CATCH trial is in the opposite direction, to the left of the direction of the anticipated consistent force field. Similar trend was observed in the perturbation group and confirmed by the group averages. The presence of the after effects here suggests that both groups had formed an internal model of the consistent force field. So although locomotor adaptation to the consistent viscous force field may have been impeded in the perturbation group, as seen in the previous slide, evidence from the CATCH trial suggests that it was not absent. Okay, this is going to be a busy slide, but it's my favorite. So we observed differences in both feed forward and feedback control mechanisms that can explain why the perturbation group had larger center of mass trajectory deviations than the control group when walking in the consistent field. In the interest of time, I'm only going to show changes in feedback control today. So one method that people use to control their medial lateral center of mass motion during walking is through the modulation of their lateral foot placement. In this trial, we can take a look at the medial lateral position of 2 steps during each trial. A first step shown in green, taken by the right foot, and a second step shown in blue, taken by the left foot. Okay, this figure shows the average medial lateral foot position for all the participants in the control group during every baseline and consistent viscous force field trial. If we take a look at the, where's my pointer? If we take a look at the right, or the first step participants took during the CATCH trials, these gigantic green spikes on this graph, when participants were unexpectedly falling to the left due to the absence of the viscous force field, we see that participants immediately adjusted their lateral foot placement and took a narrower step. The response to the CATCH trial most clearly illustrates that the control group made substantial and immediate modulations to their foot placement in response to changes in the external environment. Okay, let's compare that to what we see for the perturbation group. This figure is a little bit different than the one we just saw from the control group because it includes the additional 30 trials with pseudo-random perturbations. Okay, so again, let's look at in green. This is the first step taken by the right foot. If we take a look at those steps occurring in the consistent viscous force field, during the CATCH trials, we do not observe an immediate change in foot placement position in response to the changing in external environment. In fact, in that first step, there's almost no change in foot placement during the right first step of the CATCH trials. However, the perturbation group did make corrections during the second step, right above that, shown in blue. This division of labor make a deterministic foot placement with a first step and then correct with a second can also be clearly seen during the pseudo-random trial. So if you look in green, that first step in the pseudo-random field, you're getting pulled left and right, but that step position isn't changing. All the corrections seem to be occurring on the second step. So why didn't the perturbation group make immediate feedback-driven modulations in foot placement? One possibility is that external uncertainty may have led individuals to rely more strongly on their internal model that was formed based on extensive experience and discount the role of feedback, which was coming from an uncertain environment. This idea is supported by the gradual adaptation of lateral foot placement we see in the viscous field. So we see, again, if we look at the perturbation group in green, that first step in the consistent viscous force field, their steps gradually get wider step by step, suggesting over time they make these changes. A second possibility is that participants selected a deterministic first step with the right foot to enhance their ability to sense the true and external environment. By not reacting immediately, participants both had more time to sample the true environment, and they were able to receive a sensory signal that was not contaminated with any neuromotor noise that would have been created if they had actively moved their limb in response to the change in the environment. Okay, so overall, what do we see? Exposure to uncertainty impeded locomotor adaptation. Participants in the perturbation group adapted a multi-step strategy to successfully accomplish the goal-directed walking task in this experiment. This strategy resulted in larger deviations in center of mass trajectory than the control group and may have incurred some additional costs. So what do we see? During the first step of the task, the perturbation group selected a foot placement based on prior experience. They also did not modulate their foot placement during this first step in response to feedback. This strategy may have enhanced their ability to accurately sample the world and correctly identify sources of movement errors. Then on the second step, they used a combination of an internal model and sensory information gathered from the first step to execute and correct their movement, bring themselves to the target. So I'll go ahead and stop there. I want to thank some of the current and former members of my lab who've contributed to this work.
All right, thank you so much, Keith, for yet another great talk in this session. Got a question from James. Do you want to ask it directly?
Sure. So Keith, this is really interesting. So I'm particularly interested in the statistics of the pseudo-random perturbations and whether participants, because I would imagine that maybe they're forming an internal model of the expectation about the perturbations in terms of their timing, magnitude, and direction. So is there any bias there in the statistics of the perturbation that can explain how they respond? Hopefully that's clear.
So this would be during the pseudo-random perturbations?
Yeah. So what kind of model should they be forming based on those statistics?
So the pseudo-random perturbations, I mean, it was variable duration, magnitude. It was changing each trial. The idea being that it was not predictable. They should not be able to form an internal model of the pseudo-random perturbations. That would be in contrast to the consistent field, which was magnitude was based purely on their forward velocity, and that was learnable. So what should you model in an inconsistent environment? I'm not sure that you do model that. I think your best bet is to adopt either an impedance control strategy, which we didn't see, or simply experience the perturbation and use feedback and then correct. And it appeared to me that was what they were doing. They went ahead and sampled during the first step and corrected during the second.
Yeah, just in some of the adaptation studies, largely upper extremity, when there are random perturbations, people sort of adapt to the mean. That's something that I might expect. That I was wondering if that might have happened.
Yeah, I think no. Well, I think the magnitude of our perturbations were quite large. And I think there was really a challenge here that they couldn't adapt during the reaching experiments. People were able to create a high enough impedance to resist perturbations in both directions. I don't think people could do that without successfully taking a very wide step in one direction, that you could successfully resist perturbations in one direction or another. So if I know I'm going to get pulled to the right, I can take a wide step, generate enough ground reaction force, foot possession to do that. If I think I'm going to get pulled one way or the other, I don't think there was a solution that people had that could eliminate a large deviation in either direction. So best thing to do seemed to be hedge your bets, take a step in the middle, don't guess, and then respond.
All right.
Thanks.
I guess I'll ask a question, and I don't know if I missed it. What were the instructions to the subjects? Like, are they trying to walk straight to reach the target? Are they trying to get there in a certain time?
They had a couple of instructions. Their goal was walk to the target. We gave them feedback about time, so they had to do that pretty briskly each trial. The amount of time it took them to get there was about the same. Other than that, it was pretty much open that they could do this as they felt most optimal. They had to step first with their right foot. There was a minor instruction not to complete based on pilot work. We've had people who first came in and didn't resist the device at all and just flew off our treadmill setup and broke load cells, etc. So in the act of preserving the lab to some degree, we gave a small instruction that they should try and resist a little bit to accomplish the task.
Yeah, I'm just asking because I was trying to figure out, like, if the error, like, what is the consequence of having an error? Because if I don't really care about the error, then why would I, adapt? That's why I was asking the question about the instructions.
Okay, I think that's a really important question. I think it's quite possible. I think this gets back to the question that was asked of Amy. What is stability? What do you want to accomplish here? And I think in this case, you have a situation in which people could use different strategies to be successful at the same task. So that they had a larger deviation, I wouldn't call that unsuccessful. I would call it a different strategy. But my guess is that there's additional costs that come with not being able to create a feed-forward plan to offset the consistent environment. If you didn't have that feed-forward plan, I think there was a higher demand on cognition that you had to really accurately pay attention and sense each step what was going on with the environment to respond. You also had to then make corrections and resist the field, which I'm guessing likely increased metabolic costs. So I think there may have been some intrinsic cost factors which might be beneficial for the individuals to form a feed-forward plan to resist the field. But if we're just saying, were they successful? I think we have to say they were equally successful with our instructions. They accomplished the task. They didn't fall over. They made it in the time that they had allotted.
All right. So we're actually at time. Let's thank all of the speakers in this session for some really great talks to share their exciting research. Christian, I'll let you take over.
Well, thank you so much, and thank you, Helen J. Huang. Please check out her published works in her laboratory down at University of Central Florida, and thank you for keeping everything on time. And thank you so much for the speakers. Just such professional and interesting talks. So many. A lot of this will probably show up in the panel. I imagine some of this discussion. So thank you all for your time. Quick programming note for everyone. As I said in the chat, we will all reconvene. The panel will reconvene at 4 p.m. sharp instead of 3:55. So 4 p.m. we will start the panel, thereby pushing back our poster sessions to 4:30. So see you at 4. For everyone on YouTube, just a reminder, we will reconvene at 4 o'clock. Thank you for participating.
Hello? Can you hear me?
Yes, we can hear you.
Ah, okay. Okay.
Yeah, so do you want to be right now? You'll be broadcast to YouTube. Just FYI, Dr. Geitenbeek. FYI, if you want to chat right now, that's fine. But just be aware. Reconvene in about 4 minutes. About 4 minutes. We'll be reconvening in a moment. I'll start pinning our esteemed speakers into the pinned positions. See, Dr. James Finley is here. All right. See, Dr. Jonathan Hurst is also here. All right. And hey, Helen Huang, also here. We got our Brady Bunch all set to go, it looks like. We'll get started in just a moment. Okay, panelists, can you hear me?
I can hear you. How about me?
I can hear you.
All right.
Yes.
I can hear everybody. Well,
check one.
Check two,
Yep.
check two. Wonderful. It looks like we're all set to go. So why delay? So thank you everyone for coming back. We're getting ready for our panel session. We're about ready to start. So let me just go straight in and start introducing our various esteemed panelists. First off, thank you all for coming. I'll start off with Dr. Helen Huang, who is at North Carolina State University. She is the Jackson Family Distinguished Professor there, and she focuses on wearable assistive devices, and it's a wonderful marriage of biomechanics and robotics. On the robotics side, we have Dr. Jonathan Hurst, a professor at Oregon State University, also co-founder and CTO of Agility Robotics. You've probably seen their robots walking around, as well as co-founder of Oregon State University's Robotics Institute. Thank you for coming, Jonathan. And finally, we have Dr. James Finley, associate professor at USC, who focuses on computational models and experimentations for both able and impaired human subjects and discerning control, which is going to be wonderful for today, I think, James. Yes, awesome. Thank you all for coming. I'll launch right into it. Just going to make this a quick and punchy panel. So I saw Dr. Keith Gordon's talk just now, and he talked about how he's inferring that maybe people are controlling some of their steps for the purposes of future sensing. So that to me that's not something I would expect. So this really gets to me the role of feedback versus feed-forward control in the weird interplay that could be there. So I'll start with Dr. Huang. I would love to hear your thoughts on how important is feedback control versus feed-forward control.
Yeah, maybe I can just start with, my expertise is on the wearable robots. So in terms of the structure of general how wearable robots control, we definitely have a low-level control. For example, you have to control the joint torque, which is the closed loop, which is a feedback control. And then quite often for a higher, the middle or maybe high-level control, how you structure those torque you applied or impedance, that's actually quite open loop. Which is basically mimicking, biomechanics or something that we already learned. Of course, if you have a human in the loop optimization, like what Steve Collins did, so then that's another layer. So on top of all these, we'll formulate another layer of closed loop control. So I think there's pros and cons for each case. I often think for kind of like open loop control is beneficial for human side. Is it because, from human side, sometimes the open loop control is more predictable. The person would know, by doing this, something would happen. And also to avoid some closed loop stability issues. So therefore, I often see a lot of wearable robots is actually structured open loop control, actually quite a successful use in the field of robotic prosthesis, for example.
Yeah, and this is great. I'm going to pivot to James in just a minute on that exact question. But the thing that you're talking about is that predictability is something that could assist people, and maybe something to think about either on the robotics or bio side. Is just that predictability of what that thing is attached to you is going to do is going to help you. Is what I'm hearing from that. Am I summarizing that properly? Sorry, that was for Helen. I apologize.
Oh,
I faked you out.
Yeah. So for example, for you use a prosthetic device, for example, and then quite often people are preferring using the passive device, and then they say, well, it's a predictable. You know, once you swing your hip, residual hip in a certain way, then you know the leg gonna go that way. But for a robotic device, you know, became intelligent. Sometimes the things are, you know, there's some controller, they have no idea, and then it happens, and you're wondering, the user would wondering like, what's going on? So unpredictable is actually quite often the patient will talk to me saying that, you know, I don't like it. I wanted to know what this device is actually doing since I'm working with this device.
So awesome. And now I really will pivot to James. I mean it this time. No, it's and so yeah, your thoughts on feedback versus feed-forward control.
Yeah, so I'll just jump in on this issue of predictability and uncertainty, because I think, you know, Keith's talk was a perfect intro to this discussion. And I want to talk about two elements of that. So you can think about the properties of your environment, in the case of Keith's study, or a system, if we're talking about robotics and exoskeletons. And that's, the system may be predictable, right? It may be deterministic, or it may have statistics that could be learned, or that you know as the experimenter. But then there's another question, another side to that, which is about learning, right? This is now the human. And so regardless of what those statistics are in your system, we need to understand how the human represents those statistics. And so this is something that we've really been interested in recently. There's a whole world of people may be familiar with literature and behavioral economics, where they deal with making decisions in the context of uncertainty. And there are several ways that people can or have been shown to do that. We can ask whether people represent probability distributions, whether they estimate, you know, the min or max of some previous experience, right? We're talking about disturbances. And I mean, there are almost sort of countless other things that have been pitched in the literature. So I think that's I find that to be a really exciting question about how people deal with uncertainty in the context of gait and balance, because that affects our ability to do predictive control. You know, aside when you can't predict, then I think you must rely on feedback. And you know, I don't want to sort of rehash things that Keith has already said, because he stated it really clearly, right? He and I both deal with populations that have sensory motor impairments, where both the sensing could be impaired. If we're talking about someone who has a stroke that damages parts of the brain that deal with perception, the motor components are also impaired, and so you might not want to rely on that feedback controller. And so you may lean more toward, you know, again, words that we commonly use, proactive, predictive, feed-forward control, because it's more predictable.
Thank you so much. And I'm going to pivot to Jonathan now on this. And so on this feedback feed-forward component, and I'll particularly point out that what I hear from James is that is this part of the process where, like, there's something attached to my body, there's something in my environment. It's either there's some statistical things for some statistical way to represent it, perhaps, but you're looking at it as just like a whole system. I imagine you have some thoughts on looking at these things as whole systems, because I was your PhD student.
Yeah, well, it's also that, you know, I do robotics and not so much prosthetics. So you know, robots, you get to know everything about the system, and you don't have to make any guesses about what the person is about to do or what the person is going to do until you're doing human robot interaction and so on. But that's very different from the prosthetic. I kind of like 2 points I'd want to sort of get to on this. One is, I'm not sure I entirely understand the difference between feedback and feed forward when it comes to the big picture of I'm designing a behavior. Certainly some things can be considered feed forward, but I don't know, a physical spring versus a proportional controller is an example of something that, you know, a physical spring could be considered a feedback controller. Certainly on a robot, there's feedback control everywhere through the current or the windings of the motors. And really, I guess the question is more choosing what information you want to act on. And so when you're generating a behavior, how do you want to modify that behavior, or when might you want to modify that behavior? And so I think an example is like, you know, when you're, I don't know, you want to apply some forces on the ground, perhaps. Do you really? You know, is it that you want to control those forces on the ground, or is it that you want to allow the set of dynamics to do what it does? I don't really know if that's a feed forward versus feedback question. It's a, where have I placed my feet? Is that, a piece of information, or what's the ground stiffness? Is that something I care about? Is that something I should measure and then act on? I don't know. And that just, unfortunately devolves into the it's complicated answer, or I don't know as an answer.
Well, that's all, we try to avoid those in panels. We try to say hot takes and assert them affirmatively. But I'll take it on, I don't know. Either James or Helen, Jonathan's coming out as a roboticist, where I can design whatever I want, but you guys are at least partly constrained to biology, perhaps even human impaired biology. So please jump in on thoughts. Or I'll ping you directly, one of the two.
Yeah. Okay, well, I think that's a really interesting one because, for human robot system, if the robot is controlled somehow use a computer, then you actually have a two controller. One is so human has a brain that is a bigger controller, and then you have your computer running there. So I think it's a very important because they actually for walking, right? So it's a dynamic. There's a safety balance, all those issues there. So how they really coordinate with each other is a big deal. And the other one is we can't. So for example, I can control a prosthetic joint, but I can't control human, can I? So that's another thing is what you can modulating even with exoskeleton. There's a couple of joints that you can control, but there are a lot of other joints is actually. You can't say this is an under-actuated system because also other joints are controlled by a human brain. But definitely the machine cannot manipulate all the state within directly, at least directly to the human.
James?
Yeah, I'll just add to Jonathan's point. I think he makes a good point, right? We, in the world of psychology, right, they often talk about, sort of the perception action coupling, right? And that we don't need to think of them as two different things. They're one and the same, right? We act to perceive based on our perceptions, we act. And these things happen in loops at various levels throughout the nervous system. And so, in some ways, drawing a distinction between feed forward and feedback can lead us to create artificial realities that maybe aren't biologically plausible. But what I will say, I like to think about making predictions, which is something that I think there's strong evidence that we do, particularly in these studies where, well, maybe we can talk about what we mean by prediction if we have time, but in studies where we do adaptation and we remove perturbations and we see that the system responds as if the perturbation was still there, I think that's some evidence of prediction, at least.
I thought of an example that kind of relates to this. It's hard to come up with an answer, but I can come up with an example, right? So with Atreus, we early on were trying to do things like, Atreus, by the way, it's a spring mass robot. It's a robot with motors behind giant springs, and we were trying to capture spring mass walking and running behaviors. And we tried a lot of things before we really got some things to work well. And some of the things that we tried were very tightly coupled feedback control, where we're trying to control the forces of the end effectors that we're applying on the world. But we really couldn't do that very successfully for various actuator dynamics reasons, for inertias and the spring bouncing in ways we couldn't really control and things like that. And what really worked well is a feed forward, just kind of a play it forward, the same way you see in biology, where we know we're going to have some thrust or some motor position or set point position that the actuators are going to move through, which is totally analogous to a muscle activation. We have a set of passive dynamics which aren't exactly like a Hill muscle model, but they're close to something like a Hill muscle model. And then we would send an activation command to our inertial springy model that was only updated per stride. And that kind of clock-based feed forward activation command in combination with the passive dynamics that we just set up with some dissipation and some physical compliance and so on in the system led to some very human-like behaviors and robust behaviors in handling all kinds of obstacles in the world. So there's an example of feedback and feed forward.
So, I think that what you said, Jonathan, before about like the what is the boundary between feedback and feed forward? You might get some great pushback on that in the spatial chat. So that'll be fun to have those discussions. So that's going to be, but I do want to take this, I want to shift it to a new topic a bit, which is actually quite related. Because you're talking about, muscle activation, Jonathan, sort of like permeating through some kind of time scale and therefore making it react more slowly. James, you're talking about, maybe adaptation. And I want to get to time scales. Okay, like the time scales of adaptation, because I'll force people to make a decision. You can't be both fast and slow, can you? I don't think so. So maybe we'll start off with James on this one, on just what are the time scales of adaptation that are really important?
All right, so we have to pick a side. So I'm going to be on the side of long time scales are far more important than we classically have thought them to be, and I will talk about that work in terms of the timescales that we analyze learning. So in classic studies of motor and locomotor adaptation, we often would give people 10 minutes of experience with some novel task and say, we're studying adaptation. This is how people adapt. Work that we've presented here before, led by Natalia Sanchez, we questioned that, right? We said, well, it seems as if we have some evidence that adaptation to tasks that we study, the split belt treadmills, may take much longer than we expect. So we thought we were making huge strides and giving people 45 minutes instead of 10 to 15 minutes. And we see that people are continuing to learn. And then, 2 hours ago, that time scale was sort of blown out of the water by Katie Poggenzy. Katie, I hope I didn't mess up your last name, but she showed now we're talking hours and days of adaptation. And so, I think in these really high dimensional control spaces, right? If we're thinking about the human, and then, parameter spaces for the exo that were at least 4-dimensional, these are super hard problems to solve. And so I think we may need to rethink a lot of, in terms of experiments, the ways in which we study adaptation and the value of these short-term exposures to things.
Yeah, so maybe we'll go to Helen next here. So yeah, I mean, you have these bionic devices. You're strapping them to people. I mean, what time scales matter?
Yeah. All right. So actually, this is interesting. We used to talk about like a control. I talk about the control loop at the beginning, right? Remember? So if you think about just operating those joints, right, generate a certain trajectory or torque profile, which that's operated like at least like a milliseconds, something like that. That's a feedback. And then we also work on, so I also work on some higher level control, like, how you use reinforcement learning to personalize this device. And then for that situation is a person walk a couple of steps and then we update the control. Mm-hmm. So in that sense, right, so that scale became like a couple of steps. And then in terms of like and then also I will talk about like a human reaction to this as well. And then also in the long term, we talk about this long-term change, like when the person walked with the device for a long time, their behavior might also change. Then that's also accumulated to maybe across the days of adaptations, right? So that's again, depend on this your specific situation, but definitely for something like immediately, like you need a stretch reflex, those things are really, you need a local processor that have to react really fast. But for reinforcement learning require a lot of computation. Maybe we can put some like a media level of processor that could do these steps. So I'm talking about the computation as well. But also we're interested in the human. So when we provide, let's say we update persistence control, actually human demonstrate an immediate change because there's a neuromechanical coupling within this like a whole body. So the human also migrating. So there's a lot of idea for example, like the echo control. And when we apply the echo control, like the persistence joint try to mimic the sound side, for example, in that situation, well, when we change the control on the persistence and the other sides, the kinematics, the dynamics also started to shift. So we became a tracing problem. So all these things are through learning. I found that it's interesting. The human also has a certain adaptation rate that somehow you have to meeting with each other.
So I want to follow up with you on that, Helen. So like, I mean, if someone had so like if you had a student who's like, it's like, what time scale should I be looking for that human adaptation rate? Like, what's your best guess? What is, you know, what do you think?
Good question. Well, depend on the project of student. If it's a reinforcement learning, then it's a couple of steps.
Couple of steps.
Yes, for I think it depends on the project. We would love to have people, you know, wear the device, you know, maybe daily, use that device every day, and then you come back to test. It is just for now, at least in my lab, hasn't had that opportunity.
Yeah. All right. So we'll move on to Jonathan here. You got to have thoughts on timescales. You work on a lot of them with your agility robotics robots.
Yeah, we've recently been really thinking about reinforcement learning, right? And reinforcement learning typically is all about what's your reward function and what's your cost function. And that's really highlighted even more the importance of the different control rates in the control hierarchy. And we're kind of working on this idea that it's not necessarily just an engineering choice. It's also just based on first principles of what's the rate at which your information is coming back at you. So for a learning system, it's the rate at what you can get a corrective or a measurement basically of whether your action was good or bad. How often can that even happen? And so for things like joint control or controlling the center of pressure under your foot, or even Katie Bill was mentioning to me on the message there that the electrical rates on motors and how much torque you can apply versus the full state control of the robot. So there's 24 kilohertz at super high rate on the motor, but then how do you know where to place your foot and whether that was good or not? You only know that once per stride. And so I think it's all about the update rate of the information content, and I think that that's somewhat universal. I think that that's true in animals, where you see, the Golgi, what is it? The
Golgi apparatus?
I think I got the wrong name. No, I'm talking about the sensors in your tendons that have the direct feedback locally right there at your muscle. And then of course there's the reflex, and then there's joint coordination control throughout your body. And then there's kind of those feed forward per stride kind of, 3-step look ahead clock cycles that are happening. And it's just interesting that we're seeing some of the same parallels when trying to come up with the control hierarchies on the robots, just trying it from first principles and then just trying things, engineering wise.
But I mean, that seems kind of almost tautological. Like, well, what do you learn? Well, you learn at the right thing, in a way that makes sense. I mean, it's hard for me to argue with that. Like, oh, it depends on what the information comes in. That's how fast you can adapt, right? I mean, I'm not saying it's bad. I'm saying that so I guess it would be a distribution of what are the important pieces of information coming in. If you had a spike over the entire time scales, where are those spikes? And I'm hearing a few things along the order of like, a few steps are important, Helen would say, or I've seen many talks out of Andy's group about, a few steps is enough to recover, from perturbations, like 2 steps is enough. I've heard those kinds of claims. But that's what I hear about in terms I wonder how much each of those like fringe cases matter, and I don't know the answer. I mean, I know that in Helen and Jonathan, you're talking about these sort of kilohertz scale robot controllers, but part of me wonders, is that really important to do? Well, I mean, you guys deal with them all the time. Is that true?
So pieces of it, right? You got to control your torques at kilohertz scale.
Sure.
Throughout the middle of stance, you want to control your center of pressure a little bit to just correct whatever errors you've made in your prior foot placement or disturbances you have. It's really useful to correct things a little bit with center of pressure. Now, maybe that's not kilohertz. Maybe that's updating it, 100 hertz or something like that is plenty. And then where you're going to place your foot is, 3 hertz or something like that. But of course, the joint coordination to get there is a little bit faster. And part of the issue too is like, how much information do you have? If you're trying to control your place through the map in your environment, and you have this kind of high level plan of where you want to go and what do you want to pick up, or what are your footsteps going to be based on your reduced order model dynamic plan, you don't want to know the current through your windings for all 27 actuators on your device. It's just too much information and you can't compute it all or handle all that information. So condensing things and using layers of reduced order models is kind of necessary.
So I do want to ping James on one last question before we get to our sort of wrap up. of like what the next big things are that I want people to take away from us, particularly students. So I mean, James, Jonathan's basically talking about sysid for robots, which we could do in components. I know you have thoughts on sysid for people. So is there something we can take away as a community from your interest in sysid for people?
Is there something to take away? I hope so. So I mean, these are really sort of ideas that we have. So what we would like to do in our work, and I know plenty of other people who are interested, like we talk about balance control during walking, and we really don't know, and we have all these sources of sensory information, right? We have, Jonathan already mentioned, proprioceptive information from muscles, we have pressure information from cutaneous sensors, vestibular, and vision, and so on, right? And so what we would like to know is how does the nervous system process that sensory information to update our actions to maintain balance? And there's been work along those lines, particularly for standing, from people like John Jacob and others for years. That work has moved a little bit into walking, but walking is just a much harder problem to solve from a system ID perspective. But we're still, we're really excited about some of the perturbation related work that we're doing. So this was, we mentioned earlier today about foot placement control, right, versus control of ankle rollover and center of mass dynamics. So we're still really interested in when those different control strategies are employed. To what extent does it depend on perturbation size? How are those control strategies modified when, again, you're in a population with sensory motor impairments? So hope to share a lot more of that work probably in one of the next editions of DW here.
Well, it's fantastic, and so we're gonna try. So I'm seeing all the questions in the chat, and I'm seeing there's causing discussion all right now, and that's amazing. I want that to keep happening. We're gonna finish off with some questions for the panelists here, and I suggest if you want to engage with the panelists to do so in the spatial chat thereafter. So just to finish up, I'm gonna actually go to we'll go to Jonathan right now. So Jonathan, what would be one takeaway that you would give to all of the researchers here, maybe some of them are very early career students, of something that they should be really keeping their eyes on right now? What should they be interested in? What should they be doing?
Okay, well, let's see. A lot of the different things that we look at how we can solve these problems are just the interesting pieces and tools. And those, change over time, and reinforcement learning is an exciting one right now. But growing up in the dynamic walking community, as I did, the thing that's been valuable has been the holistic view of thinking about what do we try as a roboticist. We're trying to design a set of dynamics. We're trying to design a behavior, and that includes passive dynamics, and includes control, and includes all the different tools that we could possibly imagine for control. And I think similarly for biomechanics, you want to use all the different tools you can to learn how does it even work. But that we've had a lot of success recently in my lab with reinforcement learning. I am a mechanical design engineer. I'm not at all a computer scientist. The only reason that we've had success with this is because I've worked with others who are experts at the computer science side. We've used fairly basic and 10-year-old and older algorithms and tools that exist, but we've kind of laid out the problem from a first principles, we understand leg and locomotion, we understand the behavior that we're trying to generate, we understand how it will react to disturbances in the world, and all the kind of thing that we discuss at this conference all the time. So understanding a depth of a tool is really useful for whatever you're in, but understanding the holistic picture of what it is that what the answer is, what's the goal, what are you trying to achieve?
Sounds like you're saying don't put yourself in a box is what I'm saying. You're not, so you never know when outside that box is going to be very helpful. That's a great lesson. I can agree with that. So Helen, I would love to pivot to you next. What's the next big thing for you? What should we be looking at?
Okay. I don't know.
You don't know?
No. I have some idea. I felt like because the dynamic walking is so broad, there's like a biomechanics, pure working on with understand the human versus like a pure robot, and I'm kind of in the middle. So I think my message is probably more useful for people who working on these wearable robots, like a robotic axle or robotic prosthesis. So I my training came from more engineering side, and I used to really working on the device control rather than understand the human. I have to say, the more I work on this, I realize the human is just cannot be ignored. So I need to understand the human. So I totally agree with Katie's talk today, saying that how the human is a big portion of this. They contribute a lot for the overall performance. Plus, our goal is to improve the human's performance. Don't forget, when we design these robots, it's helping them, helping human. So I would say the next thing would be how we can really generate this human-robot coordination, the symbiotic relationship between the machine and the human. There's a multiple way we can do that. Using some learning or co-adaptation would be one way, but also, neural control, for example, directly integrated with the human's nervous system, maybe one way to go. So that's my message is, yes, take care of both sides, human and the machine.
And neural control might be one of those ways, is what you're saying.
Yes.
That's what.
Yes.
Thank you so much. Thank you for the and we'll finish with James here. So James, big questions, big things for you. What say you?
Yeah. So for us, I'm primarily interested in these inverse questions, right? We're trying to take a system that already exists and understand how it works, and that's notoriously hard and ill-posed in many ways, but I still find it to be the most interesting type of science, so we'll stick there for a while. In particular, I'll talk about drift in a moment, but I work in the physical therapy department as an engineer, and this question of what should the goals of physical therapy be for someone who's had a stroke, I find really interesting. I think classically, it's focused a lot on what people call observationally normal walking patterns. So having someone look as if have someone's gait who's had a stroke look like someone's gait who has not had a stroke. But there are many reasons why that may no longer make sense given the sensory motor impairments that exist. So we're really interested in trying to understand how do you define objectives for therapy, and that's going to drive a lot of our work moving forward. And then to kind of wrap up, I think, my experience in the dynamic walking community has been really great over the years. One thing that has happened for me, so I'm a mechanical engineer who just drifts. We talked about time scales. So I have a very slow time scale of drift. I'm now really interested in, like I said, behavioral economics. So if that's your personality, go for it. There's lots of really interesting science in all these domains. This meeting can be intimidating because you feel like you may have to be an expert in robotics and human biology, but you don't. Find something you really enjoy and just go for it. I'll stop.
Well, I certainly can endorse doing what you love, but I also for very selfish reasons endorse the last point you made about basically what do we care about? Is it normalcy? That's what I'm hearing from you, which is about like what should we be striving for? In rehabilitation, which leads us beautifully into our next episode. I couldn't plan it better myself, James, which is going to be all about tasks and objectives. It's going to be on July 15th, the same format as before. And so here we're going to wrap our panel. I want to thank you all for sort of discussing stuff with each other and putting up with my fast-paced questioning style. You're the best. Thank you all for coming. Let's give them all a round of applause.
Yeah, thank you, Christian. This was excellent.
Yes, thank you for having
Thanks
me.
for hosting us, and this was wonderful.
Thank you so much. So as this is the end of our broadcast program today, the rest of it will be in the spatial chat, and I can post the spatial chat link yet again in case you need help finding it. Feel free, if our panelists are milling about, you disagree with them, let them know. I know they love discussion, so I think this will be a lot of fun. And our poster sessions will start in approximately like 3 minutes. So please check out all these great posters. So many rooms of them, and interact. And what a great time to learn. And thank you all. Thank you also to the other organizers, Dr. Greg Sawicki's lab, and all of the lab organizers. Thank you all for your time, and you all have a wonderful weekend.
You too. Thank you.
All right, YouTube, thank you so much for sticking around and asking your questions. We'll be doing the same format on July 15th for the Task and Objectives Episode 3 of Dynamic Walking. So you all have a wonderful week.